In the boundless darkness of space, among swirling galaxies and explosive stellar nurseries, there exist places of haunting silence. These are not the thriving clusters brimming with collisions and light, but rather the aftermath, the ancient graveyards of galactic battles long past. Here, only one galaxy reigns, bloated from consuming its rivals, sitting still in the quiet center of a dying neighborhood. Surrounding it, faint companions, a whisper of what once was, and a soft but searing X-ray glow, the last trace of ancient heat. These are the fossil galaxy groups, and they are among the most enigmatic and lonely structures in the cosmos. Frozen in time, ancient, and still radiating the memory of a violent youth. But before we continue, subscribe to the channel so you don't miss out on any of these videos. Fossil galaxy groups are unique structures in the universe, and to appreciate them, we must first understand what a galaxy group is in general. Most galaxies in the universe are not isolated. They form part of larger systems known as galaxy groups or clusters, where multiple galaxies are bound together by gravity, constantly interacting, merging, and sometimes colliding. These groups can be dynamic, chaotic, and full of activity. But fossil galaxy groups are not like this. They are what remains when all that activity dies down. A fossil galaxy group begins its life like any other group, a collection of galaxies, sometimes dozens, orbiting each other within a common gravitational well, embedded in a dark matter halo. But over time, gravitational interactions cause the smaller galaxies to spiral inward toward the center. They interact. They merge. They collide. And gradually, many of them disappear, subsumed into a single massive galaxy at the heart of the group. The result is striking. At the core of a fossil galaxy group is one gigantic elliptical galaxy, often significantly brighter and more massive than any remaining companions. Surrounding this colossus is a faint halo of smaller galaxies, often dwarf galaxies, but noticeably absent are any other large, bright members. The environment has gone quiet. New mergers are rare. Star formation has often ceased. The drama is over. But there's another critical ingredient, the gas. Fossil groups are filled with an extended halo of very hot gas, reaching temperatures of millions of degrees. This gas emits strongly in X-rays and is often more luminous in X-rays than the visible light from the few remaining galaxies. This glowing envelope is not a sign of new life, it is a relic. A reminder of the energy released during those ancient mergers. It's the hot breath of a system that once seethed with movement, but now lies still. What's perhaps most fascinating is how these structures appear in different wavelengths. In optical light, they can be deceptively mundane, a big elliptical galaxy, a few dim companions, nothing dramatic. But when observed in X-rays, using space telescopes like Chandra or XMM Newton, they suddenly become spectacular. The massive gas halo glows like an invisible fire, revealing the full extent of the structure, and the history hidden within. Astronomers define fossil groups not just by appearance, but by measurable criteria. One of the key indicators is a brightness gap, specifically, a gap of at least 2 magnitudes between the brightest galaxy and the second brightest galaxy within a certain radius, typically 500 kiloparsecs. That's roughly a 6-fold difference in brightness, indicating that no other large galaxies are left in the group. They've already merged into the central one. Additionally, the X-ray luminosity must exceed a certain threshold. That confirms the presence of hot intergalactic gas that hasn't cooled or condensed into new stars, but instead continues to radiate quietly, a glowing remnant of past turbulence. In essence, fossil galaxy groups are not fossils because they are dead. They are fossils because they have preserved a moment in cosmic evolution, a phase where galaxies merged rapidly and then stopped, where the surrounding environment became inhospitable to new activity, where the conditions for change were replaced by a long, lonely equilibrium. They are not necessarily rare, but they are hard to recognize. Without the telltale X-ray glow, many of them would simply look like a big galaxy surrounded by almost nothing. But they are more than that. They are the end stage of a long journey. A galaxy group that has lived fast and burned bright, and now rests in its twilight. These systems challenge our understanding of how galaxies evolve. They show us what happens when galactic interaction runs its course. They give us clues about the role of dark matter, the fate of hot gas, and the ultimate quieting of star formation. In many ways, they represent what our own local group might become in the far future, when the Milky Way and Andromeda have merged, and all our companions are gone. Fossil galaxy groups are the silent witnesses of the universe's youth. And to look at them is to look at memory itself, the memory of a cosmos that was once more chaotic, more violent, and full of light. It begins with their striking appearance. When astronomers first observed these unusual systems, they noticed something peculiar: a single, extremely luminous elliptical galaxy sitting alone in what should have been a vibrant galactic community. Surrounding this central titan were only faint, minor galaxies, and no bright neighbors of comparable size. Yet when viewed in X-rays, the group was anything but empty. A massive halo of hot gas surrounded the entire region, the kind of glow typically found in much larger galaxy clusters where dozens or even hundreds of galaxies reside. Something didn't add up. This paradox, the presence of bright, extended X-ray emission without a crowd of galaxies to match, led researchers to a compelling realization. What they were seeing wasn't an anomaly, but the final stage of a once-active galaxy group. All the bright, massive galaxies that should have been there had likely merged into the central elliptical, one by one, over billions of years. The result was a system that looked quiet and simple, but carried the scars and memory of intense galactic violence. Thus, the term fossil group was born. Like the skeletal imprint of a dinosaur preserved in stone, these galaxy groups offered a preserved record of the past. They were relics, not dead, but no longer evolving in the usual way. Their current structure was the frozen result of a long history of mergers and interactions, and they had since reached a phase of deep cosmic stillness. What's particularly poetic about the term is that it captures both the past and the present. These systems are fossils not because they are inactive today. After all, the hot X-ray gas still glows brightly, and the central galaxy may harbor an active supermassive black hole. They are fossils because their evolutionary path has effectively concluded. New galaxies are no longer arriving. Mergers have ceased. The once chaotic environment has gone quiet. In some cases, the brightness gap between the central galaxy and its next brightest neighbor is so vast that it appears almost absurd. A 2-magnitude difference in brightness translates to the central galaxy being more than 6 times brighter than any other galaxy in the group. That alone suggests a significant period of isolation and a long history of cannibalistic mergers. The fact that the X-ray halo remains, a ghostly signature of the original galaxy group's gravitational binding energy, only reinforces the impression that we're looking at something ancient. And it's not just the visible elements that tell this story. The dynamics of the hot gas, the lack of cold gas for star formation, and the smooth structure of the central galaxy all point to an aged, evolved system. The fossil group has settled. It has reached a kind of cosmic equilibrium, no longer disturbed by the inflow of new material or the fireworks of galactic collisions. Even the location of fossil groups within the cosmic web may reflect their age. Many are found in relatively isolated regions of space, not near dense clusters where new galaxies can fall in and stir things up, but rather in the outskirts, where quietness allows the story of the past to linger. It's as if the universe itself has allowed these places to be preserved, undisturbed, like amber trapping the shape of a once living thing. So, the name fossil is not a dramatic flourish. It is a precise descriptor. These galaxy groups are cosmic fossils, recording a moment in galactic history that has long since ended. They allow astronomers to study the outcome of galaxy group evolution at its most extreme, a single giant galaxy standing in the stillness, surrounded by the memory of those it absorbed. To gaze at a fossil group is to witness the echo of ancient collisions, the residue of galactic cannibalism, and the slow cooling of a once fiery neighborhood of stars. It is to see the end of a story, still illuminated by the faint glow of long-finished chapters. What sets fossil galaxy groups apart from other systems in the cosmos is not just their origin or fate, but the very clear, measurable fingerprints they leave behind, distinctive traits that act like cosmic signatures. These traits form a pattern so consistent that astronomers can identify fossil groups across vast distances simply by recognizing their hallmarks. And while they may appear deceptively simple at first glance, the layers of structure, from starlight to X-ray glow, reveal an evolutionary history both violent and serene. The first and most obvious hallmark is the central galaxy itself, a giant elliptical behemoth that dominates the entire group. It is not just the largest galaxy in the area, it is far and away the brightest. In fact, one of the formal criteria used to define a fossil group is a brightness gap of at least 2 magnitudes between this central galaxy and the second brightest galaxy within a defined radius, usually around 500 kiloparsecs. That gap is not a trivial one, it translates into a brightness difference of more than 6 times. Such a disparity does not happen by chance. It signals a system that has gone through multiple mergers and consumed nearly all of its massive companions. The result is a solitary monarch sitting on a throne built from the bones of its rivals. This central elliptical galaxy tends to have an old stellar population, a sea of ancient stars that formed long ago and have since aged into cooler, redder hues. There is usually little to no star formation occurring, no dust lanes or spiral arms, no hot young blue stars. Its shape is smooth, spheroidal, and massive, often extending over hundreds of thousands of light years. It radiates primarily in the visible and near-infrared, its glow coming from stars that have long since stopped being born. The second key trait is the lack of other bright galaxies in the vicinity. While there may be a smattering of faint dwarf galaxies scattered across the group, they are generally small, dim, and widely spaced. What's absent is just as important as what remains. The usual collection of large spiral and elliptical galaxies seen in typical galaxy groups is simply gone. The environment is sparse, quiet. This emptiness is what makes the central galaxy's dominance so stark, and why the term, fossil, feels so appropriate. The bustling galactic community that once was is no longer. Only ghosts remain. But perhaps the most mysterious and striking feature of all is the extended halo of hot gas that surrounds the group. This is not visible in ordinary optical telescopes. It only becomes apparent when viewed in the X-ray part of the spectrum, using instruments like the Chandra X-ray Observatory or XMM Newton. The halo can stretch for hundreds of thousands of light years, enveloping the entire system in a diffuse, invisible cocoon of superheated gas. This gas is not merely warm. It reaches temperatures of tens of millions of degrees Kelvin, glowing brightly in X-rays. And its presence tells a deeper story. This is the leftover intergroup medium, the intergalactic plasma that once filled the space between multiple galaxies. As those galaxies merged and the group matured into its fossil phase, this gas was not absorbed. It remained, gravitationally bound to the system, heating up as energy was released during the galactic collisions. It now floats in equilibrium, a luminous echo of past violence, and one of the strongest clues that this group is more than just a lone elliptical galaxy with faint companions. In fact, it is this X-ray halo that often serves as the initial trigger for discovery. Astronomers scanning the sky in X-rays may find a large, bright source that looks like it should belong to a rich galaxy cluster, only to find, on closer inspection in optical light, that there is just one big galaxy and no large companions. That disconnect between the X-ray brightness and the optical population is one of the clearest flags that a fossil group has been found. Another important hallmark, though more subtle, lies in the velocity dispersion of the group, essentially a measure of how fast the remaining galaxies are moving relative to one another. In fossil groups, this dispersion is often lower than in rich clusters, reflecting the fact that there are fewer massive galaxies left to stir up the gravitational pot. The system has settled into a relatively calm state, with only minor galaxies orbiting the central giant, and no large gravitational disruptions left to occur. Put together, these traits create a fingerprint that is unmistakable. One enormous, dominant elliptical galaxy. A severe lack of other bright galaxies. An expansive, glowing X-ray halo. An ancient stellar population. Little to no star formation. A history written in mergers, and a present defined by stillness. They are the bones, the ash, the quiet footprints left after the fire of creation has burned out. Detecting fossil galaxy groups is not as straightforward as pointing a telescope at the sky and spotting a lone galaxy. These ancient structures do not reveal their full story in visible light alone. In fact, if astronomers relied only on optical observations, many fossil groups would go unnoticed, dismissed as ordinary elliptical galaxies sitting in relatively empty patches of space. Their true nature is hidden, layered beneath wavelengths invisible to the human eye. To uncover them, astronomers must look beyond, into the X-ray universe, where the whispers of ancient galactic violence still glow. The key to discovering fossil galaxy groups lies in multi-wavelength astronomy, the ability to observe celestial structures across various parts of the electromagnetic spectrum. Among these, X-ray astronomy is by far the most critical for identifying fossil groups. That's because one of their most defining traits, the extended halo of superheated gas, shines primarily in the X-ray band. This gas, often reaching temperatures of 10 to 100 million Kelvin, is invisible to optical telescopes but becomes luminous in the high-energy part of the spectrum. Enter space-based X-ray observatories like NASA's Chandra X-ray Observatory and ESA's XMM Newton. These powerful instruments orbit above Earth's atmosphere, which blocks most X-ray radiation from space, thankfully for us, but frustrating for ground-based astronomy. From their positions in orbit, these telescopes scan the sky, detecting X-rays from supernova remnants, black holes, neutron stars, and crucially, from the vast, diffuse gas that permeates galaxy clusters and groups. When fossil galaxy groups are surveyed in X-rays, they often exhibit a bright, centrally concentrated emission, sometimes rivaling the luminosity seen in much larger galaxy clusters. But unlike clusters, where that emission typically correlates with a large population of galaxies, fossil groups show an unusual mismatch. Lots of X-ray light, but very few galaxies. That contrast raises immediate questions, and prompts astronomers to dig deeper using optical and infrared surveys. Once an X-ray bright candidate is found, astronomers follow up with telescopes like the Hubble Space Telescope, the Subaru Telescope, or ground-based survey instruments like those used in the Sloan Digital Sky Survey (SDSS). These tools provide high-resolution images and spectral data, allowing astronomers to identify the galaxies in the vicinity of the X-ray source. If they find a massive central elliptical galaxy and very few bright companions, especially if there's a 2-magnitude brightness gap, they begin to suspect they're looking at a fossil group. Redshift measurements then confirm whether the galaxies in view are actually part of the same structure or just aligned along the line of sight. This step is essential. A background or foreground galaxy might appear near the central elliptical, but not be gravitationally bound to it. By measuring the redshift, the degree to which light has been stretched by the expansion of the universe, astronomers can determine whether all the galaxies reside at the same cosmic distance, and thus belong to the same group. Sometimes, astronomers also use Sunyaev-Zeldovich effect observations to probe the hot gas in these systems. This effect, detectable through sensitive microwave observations, occurs when cosmic microwave background (CMB) photons pass through hot electron clouds and gain energy. Fossil groups with significant gas halos can imprint faint but detectable signatures in the CMB, further confirming their structure and mass. Gravitational lensing, the bending of light by massive objects, can also provide mass estimates for the dark matter halos enveloping fossil groups. Though subtle, weak lensing techniques have been used to infer the presence of large dark matter structures in systems that visually appear sparse. These measurements help confirm that fossil groups still possess the mass one would expect of a mature galaxy group, even if they no longer host many bright galaxies. Another technique involves comparing fossil group candidates against computer models and galaxy catalogs. Surveys like the 2-Mass Redshift Survey, the Dark Energy Survey, and future missions like Euclid and the Nancy Grace Roman Space Telescope promise even more refined searches, with AI-assisted algorithms scanning through massive datasets to flag systems with fossil-like properties. Despite all this, detecting fossil groups remains a subtle science. It's not just about finding a big galaxy, it's about the context, the surrounding emptiness, the ancient X-ray glow, the isolation, the silence. Each detection is like uncovering a time capsule, long buried, requiring tools tuned not to brightness, but to energy, temperature, and gravitational traces. In the end, it takes a team of instruments, X-ray eyes in orbit, optical surveys on mountaintops, redshift data from spectrographs, and algorithms trained to spot silence where there should be sound. Only then can we begin to recognize these cosmic fossils, not as isolated anomalies, but as pages from a history book written in the stars. One of the most intriguing puzzles surrounding fossil galaxy groups is their unexpectedly bright X-ray halos, emissions so powerful and expansive they can rival those found in much larger galaxy clusters. And yet these fossil groups contain far fewer visible galaxies. How can something that seems so visually empty radiate so much energetic light? The answer lies in a story of heat, gravity, and memory, a tale preserved in gas hotter than any star, still glowing long after the galactic drama has ended. To understand this glow, we must first consider what X-rays actually reveal in astrophysical terms. In the cosmos, X-ray emissions are typically associated with extreme temperatures, often tens of millions of degrees Kelvin. In galaxy groups and clusters, these emissions originate from a diffuse, ionized plasma known as the intragroup or intracluster medium. This gas is not part of any one galaxy. Instead, it fills the space between them, tracing the shape and depth of the group's gravitational well. Heated by gravitational collapse and the violent interactions of galaxies, this plasma emits a steady X-ray signal detectable by space telescopes. In fossil galaxy groups, this gas has an unusual story to tell. The high X-ray luminosity in these seemingly quiet systems is a fossilized record of intense past activity. In the early stages of a fossil group's life, when it was just an ordinary group of galaxies, interactions and collisions were frequent. Galaxies passed close by, tugging on each other with tidal forces. Some collided head-on. As they merged, their stars often passed through one another unharmed, but their gas did not. Galactic gas clouds slammed into each other, triggering massive shock waves. These shocks heated the gas to extreme temperatures, ionizing it and driving it out of individual galaxies into the intragroup space. The energy released during these mergers helped raise the temperature of this newly liberated gas to millions of degrees. But that's only half the story. Once the system had devoured nearly all of its large galaxies and formed a single dominant elliptical galaxy, the mergers ceased. New galaxies stopped falling in, and the cosmic violence ended. What remained was the gas, still hot, still glowing, held in place by the group's massive gravitational potential. And since no new large galaxies were arriving to stir things up or introduce fresh material, the gas settled into a long-lasting, stable configuration. This hot gas acts like a thermal memory of the group's past. It doesn't cool quickly. In fact, the cooling time of this plasma often exceeds the age of the universe in some regions. Without disturbances, it remains suspended in hydrostatic equilibrium, radiating steadily in X-rays. And because the group isn't forming many new stars, there are no supernova-driven winds or active galactic fountains to stir or deplete this medium. The environment is quiescent. The heat lingers. The glow endures. Another factor contributing to the brightness is the concentration of this gas. In fossil groups, the lack of ongoing mergers allows the gas to settle more smoothly into the gravitational center. This often results in a centrally concentrated X-ray profile, where the density, and thus the brightness, of the emission increases dramatically toward the core. This sharp core can make fossil groups deceptively luminous in X-rays, even more so than some loosely bound galaxy clusters with twice the number of galaxies. What's even more fascinating is that the X-ray properties of fossil groups, their luminosity, temperature, and spatial extent, often appear similar to those of systems with far more visible galaxies. This raises a critical question. If two systems have comparable X-ray halos, but one is filled with bright galaxies and the other has only one, what happened to the rest in the fossil group? The answer reinforces the idea that fossil groups are not born quiet, they become that way. They've lived through a storm of mergers, and the gas is what remains of that storm. Moreover, the composition of the hot gas can reveal insights about the group's past. Elements like iron, silicon, and oxygen are present in this plasma, synthesized in the hearts of stars and released into space through supernova explosions. Their presence in the intergroup medium confirms that many stars lived and died in these galaxies before the mergers, enriching the gas and leaving behind a chemical fingerprint of the group's stellar history. In some cases, astronomers detect subtle temperature gradients within the X-ray halo, indicating past episodes of activity, possibly outbursts from central supermassive black holes or smaller-scale merger events. But in general, fossil groups have remarkably smooth and relaxed X-ray profiles, consistent with their status as dynamically settled systems. The chaos is over. Only the heat remains. So the mystery of the bright X-ray halos is not a mystery at all, once the fossil group's past is fully understood. These glowing veils of gas are the lingering afterglow of a time when galaxies collided, stars exploded, and the intragroup medium was ignited like a slow-burning flame. In the darkness of deep space, that flame still glows, not as fire, but as memory. The striking emptiness of fossil galaxy groups poses one of their most captivating puzzles, a mystery not of what's present, but what's missing. In systems that still radiate the mass and energy of full-fledged galaxy groups, where is everyone? Why does one galaxy dominate so completely, and what happened to all the others that were supposed to be there? This is what astronomers refer to as the missing galaxies problem, the observed absence of multiple bright galaxies that should be present in a gravitational system of such size and mass. To be clear, fossil galaxy groups still contain mass on par with typical galaxy groups. Their dark matter halos are vast and deep. Their hot gas halos glow in X-rays as though they encompass an active galactic neighborhood. But when viewed in optical light, they show only a single luminous elliptical galaxy at the center, and a faint smattering of tiny companions. It's as though the group had been picked clean, or more accurately, devoured from within. The leading explanation for this eerie absence is that the missing galaxies are not gone in the sense of having vanished from existence. Rather, they've been consumed, gradually but relentlessly, by the central galaxy through a process known as galactic cannibalism. Over the course of billions of years, gravitational forces drive satellite galaxies to spiral inward, lose momentum, and ultimately merge with the dominant galaxy at the core. This process begins early in the life of a galaxy group, when galaxies are still relatively close together and interacting regularly. Each galaxy exerts a gravitational pull on the others, and as they orbit the group's common center of mass, some lose energy through a process called dynamical friction. This phenomenon occurs when a massive galaxy plows through the surrounding dark matter and gas, creating a wake of increased density behind it. This wake pulls back on the galaxy, gradually slowing it down. As it loses momentum, it spirals inward toward the group's center, eventually merging with the central galaxy. The larger and more massive the satellite galaxy, the more rapidly it loses energy and falls inward. Over time, the biggest galaxies fall victim first, plunging into the gravitational center and merging with the growing elliptical at the core. These mergers are not explosive cataclysms. In many cases, they are dry mergers, meaning they occur with little available gas and generate little new star formation. Instead of birthing brilliant new stars, these mergers mostly add mass and older stars to the central galaxy, making it grow larger, redder, and rounder. Each merger erases a galaxy from the group's population count, but their stars don't vanish. Instead, they become part of the swollen, smooth halo of the central elliptical, contributing to its luminosity, its mass, and its extended structure. As this process repeats again and again, the central galaxy becomes a kind of graveyard for its former neighbors, a composite of dozens of once separate galaxies whose individual identities have been lost in the merger. Observational evidence supports this scenario. Many fossil group central galaxies are extraordinarily massive, with stellar envelopes stretching far beyond those of ordinary ellipticals. Some exhibit faint shells or ripples in their outer regions, subtle scars left behind by past mergers. Others show a surprisingly smooth and spherical shape, a typical feature of systems that have experienced multiple minor and major mergers over time. But the puzzle deepens when we consider the lack of replenishment. In many active galaxy groups and clusters, even as galaxies merge, new ones are often drawn in from the surrounding cosmic web. Streams of dark matter and gas bring in fresh material, preventing the group from reaching a fossil phase. In fossil groups, this infall has essentially stopped. The system has become dynamically isolated, a cosmic cul-de-sac with no new galaxies entering to replace those that have been consumed. This isolation accelerates the road to fossilization, because once the larger galaxies have merged, there are no more left to disturb the gravitational quiet. Another factor contributing to the absence of galaxies is the heating of the intragroup gas during mergers. As the group evolves, repeated collisions and energetic processes inject heat into the gas that lies between galaxies. Once heated to extreme temperatures, this gas becomes resistant to collapse. It no longer cools efficiently, which prevents it from forming new stars and new galaxies. Over time, the group becomes both dynamically and thermally quenched. No new galaxies arrive, and no new galaxies can form internally. Interestingly, some fossil groups do retain a small population of dwarf galaxies, faint, low-mass galaxies that are too small to have yet been absorbed or too far from the center to be affected. These dwarfs continue to orbit quietly, often in elongated, stable paths far from the gravitational reach of the central elliptical. But even they may not survive indefinitely. Given enough time, they too may fall inward and be digested by the central galaxy, or they may simply fade from visibility, their star formation quenched by the hot, hostile environment. Computer simulations lend strong support to this model. Cosmological and body simulations, numerical models that follow the motion of particles under the influence of gravity, have shown that galaxy groups with early, rapid formation histories and minimal external infall are more likely to become fossil groups. In these simulations, the largest galaxies fall in and merge quickly, forming a massive central object. Over billions of years, this object grows larger and more dominant, while the group as a whole becomes increasingly quiet. Eventually, it meets the observational criteria for a fossil group: a large central elliptical, a wide brightness gap, and an extended X-ray halo. It's also worth noting that some fossil groups may not be quite as devoid of galaxies as they seem. Rather, the remaining galaxies may simply be too faint to detect with current instruments. As observational technology improves, especially with upcoming telescopes like the James Webb Space Telescope, Euclid, and the Nancy Grace Roman Space Telescope, we may begin to uncover ultra-faint dwarf galaxies or remnants that had previously been invisible. But even these additions won't change the overall picture. The group is no longer evolving in the traditional sense. The age of mergers is over. The silence has begun. So, the missing galaxies are not missing in the sense of absence. They are still there, but they are no longer separate. Their stars orbit within the vast body of the central galaxy. Their gas is part of the glowing halo. Their structure is erased, but their history remains, written into the mass, shape, and chemistry of the elliptical that sits alone at the group's heart. This is what makes fossil galaxy groups so powerful as natural laboratories. They allow us to see the outcome of galactic cannibalism in its final form, not just theoretically, but as a living, observable entity. They are the result of consumption, isolation, and the inevitable quieting that follows. A cosmic echo of communities that once bustled with galaxies, now reduced to one. When we look at fossil galaxy groups, we are peering deep into the past, not just spatially, but temporally. These cosmic structures are not recent formations. Their roots trace back billions of years into the universe's history. Understanding when fossil groups formed is crucial because their age carries the fingerprints of the earliest and most transformative epochs in galaxy evolution. In essence, fossil groups are some of the universe's most ancient survivors, massive relics forged in the fires of galactic merger events that occurred more than 4 billion years ago, and in many cases, even earlier. To construct the formation timeline of fossil groups, astronomers rely on a combination of observational data, stellar population analyses, chemical composition, and high-resolution cosmological simulations. All of these tools point to a common conclusion: fossil galaxy groups are old. In fact, their formation begins when the universe was only a few billion years old, a time when galaxies were still rapidly assembling and merging at a furious pace. Cosmological simulations suggest that many fossil groups began forming in dense regions of the early universe where dark matter halos collapsed quickly. These halos, which provide the gravitational scaffolding for galaxies, are crucial to the development of large-scale cosmic structures. In regions of slightly higher than average density, gravity pulled together dark matter and gas more efficiently, triggering early galaxy formation and accelerated growth. It is in these environments that fossil groups likely found their origins. By around 8 to 10 billion years ago, just 3 to 5 billion years after the Big Bang, the progenitor galaxies of today's fossil groups had already begun merging. Multiple large galaxies in a given halo would gravitationally interact, drawing closer together over time. This early merging phase was turbulent and energetic. Galaxies collided, exchanged material, and produced bursts of star formation, leaving behind enormous quantities of hot gas and triggering the first signs of what would eventually become a fossil group's X-ray halo. Over the next few billion years, a critical shift occurred. The group reached a point where nearly all the large galaxies had merged into a single massive elliptical, and the rate of new galaxy infall diminished dramatically. This infall, the process by which new galaxies are pulled into a group from the surrounding cosmic web, plays a vital role in determining whether a galaxy group continues to evolve or transitions into a fossil state. In fossil groups, this process slowed to a trickle, allowing the system to stabilize and fossilize. By the time the universe was roughly 8 to 10 billion years old, or about 4 to 6 billion years ago in cosmic terms, many fossil groups had already taken on their defining characteristics. The central elliptical galaxy had absorbed most of its bright companions. The X-ray halo had become pronounced, fed by merger activity but now stable in its thermal profile. And the remaining dwarf galaxies drifted silently in orbits far from the center, rarely interacting or disturbing the peace. Stellar population studies support this timeline. By analyzing the light from stars in the central elliptical galaxies of fossil groups, astronomers can estimate the average age of those stars. These studies consistently find that most of the stellar mass in fossil groups' central galaxies formed over 8 billion years ago. This indicates that the last major episodes of star formation, likely fueled by earlier gas-rich mergers, ended long ago. What we see today is a mature population of old, red stars, slowly aging in place, with no significant new generations to replace them. This also fits with what we know about the chemical composition of the hot gas and fossil groups. The presence of metals like iron, oxygen, and silicon in the X-ray halos shows that supernovae from earlier stellar populations enriched the gas long ago. These elements take time to build up through stellar evolution, and their abundance in fossil groups further reinforces the idea that these systems are ancient, with little recent stellar activity. In fact, some studies suggest that fossil groups may be among the first large-scale structures to form in the universe. Because they collapsed and merged so early, they may have reached a kind of gravitational and thermal equilibrium before other galaxy groups even fully assembled. In a cosmic sense, they are overachievers, systems that evolved quickly and then became frozen in their final form while the rest of the universe continued to grow and change. It's also telling that the rate of fossil group formation appears to decline with time. In the current epoch, the last few billion years, fewer new fossil groups are forming. This is likely due to the universe's accelerated expansion, which has stretched the cosmic web and reduced the rate at which galaxies fall into groups. The conditions that led to fossil group formation, dense, early collapse with minimal later infall, are becoming less common. This makes existing fossil groups even more valuable as natural records of cosmic history. They are not just old, they are reminders of a different universe, one more compact, more interactive, and more violently creative. So, when we look at a fossil group today, we are seeing a snapshot of something that stopped evolving long ago. The galaxies that once spiraled toward the center have long since vanished into a single, massive form. The hot gas that was stirred and shocked by early collisions now lies in quiet thermal balance. The stars, born in the energetic youth of the universe, now drift in slow orbits, their nuclear furnaces dimming with age. And in all this stillness, we find one of the most powerful insights astronomy can offer, the ability to look not just across space, but back through time, to an era when the universe was young and galaxies were just beginning to write their stories. Fossil groups, then, are not just structures. They are chronicles. They tell us not only what the universe looks like now, but what it used to be. Their formation timeline speaks of rapid early development followed by long-term dormancy. And in their silence, they preserve the echoes of an ancient time when the cosmos was loud with light, collision, and creation. In the grand narrative of cosmic evolution, fossil galaxy groups represent the final chapter in a story defined by motion, interaction, and transformation. They are the quiet epilogues of once thriving communities, galactic ecosystems that burn brightly with collisions, mergers, and bursts of star formation, only to reach a point where everything fell silent. These systems are not paused or dormant in the way a star might flicker between activity cycles. They are, by nearly every meaningful measure, complete. The term often used to describe them is dynamically evolved, and it implies something far more profound than mere stillness. Fossil groups have not only settled, they've settled permanently. They are the end states of galaxy group evolution, where the processes that typically drive galactic change have all but ceased. No new large galaxies are falling in. No star-forming gas is being stirred. No major gravitational interactions are occurring. The fireworks have finished, and the embers are fading. In most active galaxy groups, motion is constant. Galaxies pass by one another in elongated orbits. Some spiral inward, others fall in from the outskirts. Interactions trigger bursts of new star formation as gas clouds collide and compress. Black holes flare with activity. Supernovae scatter heavy elements through the intergalactic medium. The group lives. It changes. It evolves. But fossil groups are something entirely different. In a fossil group, that once chaotic dance has slowed to near stillness. The massive galaxies have merged, reducing the group to a single dominant elliptical with a sparse collection of tiny, dim companions. The hot X-ray gas, once churned by the violence of galactic collisions, now floats in a serene state of thermal equilibrium, undisturbed by infalling objects or internal turbulence. The conditions for change, the triggers that drive transformation, have all vanished. One of the clearest signs that a fossil group has gone quiet is the lack of star formation. In most galaxies, star formation requires cold molecular gas, clouds of hydrogen dense and cool enough to collapse under their own gravity and give birth to new stars. But in fossil groups, this gas is almost completely absent. Over billions of years, the repeated mergers that built the central galaxy also heated and dispersed its internal gas. The remaining intergalactic gas is far too hot to cool down and condense. It remains ionized, glowing in X-rays, locked in a state that actively prevents new stars from forming. This process is often referred to as quenching, and in fossil groups, it is remarkably effective. The environment becomes hostile to star formation on every level. The gas is too hot. The pressure is too high. There are no new cold clouds being introduced from the outside. Even if a dwarf galaxy manages to survive in the outer halo, its internal gas is slowly stripped away by the hot surrounding medium, a process known as ram pressure stripping, until it, too, becomes a lifeless collection of old stars. Without new gas, without new stars, and without new galaxies, the system slowly fades in optical brightness. The central elliptical remains massive and luminous, but its light is composed entirely of ancient stars, red, dim, and aging. These stars have exhausted their fusion potential, or are slowly burning through the last reserves of helium and hydrogen. Over time, the galaxy becomes redder and fainter, its stellar population drifting further into cosmic senescence. Meanwhile, the lack of mergers has structural consequences as well. In more active groups, galaxies frequently pass near one another, tidally distorting each other's shapes and triggering waves of internal activity. In fossil groups, these events are rare. The galaxies that remain are so widely spaced and so low in mass that their gravitational influence is minimal. The central galaxy, massive as it is, sits in a state of isolation, unchallenged, undisturbed. It is as though the gravitational theater has emptied out, leaving a single performer alone on stage. This gravitational quiet extends to the group's large-scale structure. Simulations suggest that fossil groups exhibit less substructure than typical groups of comparable mass. There are fewer clumps of material, fewer signs of recent infall, and fewer disruptions in the X-ray gas profile. Everything appears smooth, stable, and spherical, the hallmarks of a system that has reached gravitational equilibrium and will likely stay that way. Even the central supermassive black hole, often a wild card in galaxy evolution, may have calmed down. In some fossil groups, there are signs that the black hole once powered a quasar or a powerful active galactic nucleus, AGN, injecting jets of energy into the surrounding gas. But in the present day, many of these black holes appear dormant. Their fuel supply, cold gas from nearby galaxies or cooling flows from the intragroup medium, has dried up. Without food, even these cosmic engines go quiet. The implications of this are enormous. Fossil groups serve as natural laboratories for studying the final state of galactic ecosystems. They allow astronomers to ask questions like, what happens when a galaxy group runs out of fuel? How does structure persist in the absence of change? Can a system become so dynamically mature that evolution effectively ends? In many ways, these groups represent what the future holds for much of the universe. As the cosmic expansion continues to accelerate, galaxy clusters and groups will become increasingly isolated. New galaxies will stop falling in. Star formation will slow and eventually cease. Over trillions of years, the universe itself may come to resemble a vast collection of fossil systems, each one a relic of a younger, more active cosmos. Fossil groups offer us a glimpse of that future. They are not the end of a process so much as the state beyond the end, a kind of cosmic afterlife, where galaxies no longer grow or interact, but simply exist. Their silence is not merely observational, it is evolutionary. It speaks of a time when the universe was denser, more violent, and more energetic, and reminds us that even in the vastness of space, nothing remains dynamic forever. The fossil group is a structure that has lived through billions of years of drama and now floats quietly through the cosmos, having reached a kind of terminal serenity. No new mergers. No new stars. No new beginnings. Only the glow of memory, the weight of accumulated mass, and the quiet hum of heat left over from a time when galaxies still danced. In the vast and mostly empty depths of the universe, there exists a galaxy that seems almost too quiet for its size, too alone for the company it keeps. Its name is NGC 1132, and to astronomers, it is one of the most iconic and puzzling examples of a fossil galaxy group ever discovered. It doesn't scream for attention with flashing quasars or luminous spiral arms. Instead, it whispers, softly, eerily, the story of an entire galactic group consumed by time, and by one of its own. Discovered and catalogued as an elliptical galaxy, NGC 1132 at first glance appears ordinary, a giant elliptical glowing calmly in the optical wavelengths. But when astronomers turn more sensitive instruments toward it, they quickly realize that this galaxy was anything but ordinary. Deep within the constellation Eridanus, NGC 1132 lies about 320 million light-years from Earth. It is surrounded not by the bustling company of other bright galaxies, but by a haunting silence, a sparse environment where nearly all of its peers have vanished. There is no rich galactic cluster, no parade of spirals or ellipticals. Just NGC 1132, massive and alone. Its visual appearance already raises questions. The galaxy is unusually large, not just in physical size, but in stellar mass. Estimates suggest that NGC 1132 is several times more massive than a typical elliptical galaxy of comparable brightness. It stretches outward with a halo of stars that hints at a history of devouring others, a galactic feast that left behind no visible trace of its victims. But what truly cemented its reputation as a fossil group was its X-ray signature. When observed with NASA's Chandra X-ray Observatory, NGC 1132 stunned astronomers with its brilliant and extended X-ray halo, one that rivaled the emissions of entire galaxy clusters. The surrounding hot gas extends for hundreds of thousands of light-years, shining brightly in X-rays with temperatures of several million degrees. This is not the kind of emission produced by an ordinary galaxy. This is the glow of an entire intergroup medium, the leftover plasma from a population of galaxies that once filled this space, now absorbed into one. This mismatch, between the apparent optical emptiness and the energetic X-ray presence, was a glaring clue. Fossil groups are defined in part by this contradiction, systems that look visually empty but radiate the thermal memory of something far larger. NGC 1132 fits that definition perfectly. Studies with Chandra and ESA's XMM Newton revealed a smoothly distributed gas halo around NGC 1132. There were no significant signs of recent mergers or active galactic nuclei stirring up the gas. Instead, everything pointed toward a relaxed, settled state. The halo had reached hydrostatic equilibrium, meaning that the gravitational pull of the group and the outward pressure of the gas were in balance. This equilibrium only arises when a system has remained undisturbed for billions of years, another fingerprint of a fossil group. Further investigations revealed additional peculiarities. Using optical spectroscopy and high-resolution imaging from the Hubble Space Telescope, astronomers confirmed the lack of bright companion galaxies within a significant radius. A few faint dwarf galaxies lingered in orbit, but none came close to matching the central galaxy in brightness or mass. The brightness gap, one of the formal criteria for defining a fossil group, was clearly met. But NGC 1132 was not just fossil-like. It became a prototype, the subject of multiple studies aimed at understanding fossil group evolution, structure, and origin. Its strange combination of isolation and mass, of stillness and thermal brightness, made it a laboratory for probing questions about galaxy cannibalism, dark matter, and group dynamics. The central question many astronomers asked was, how did this system come to be? Simulations suggest that galaxies like NGC 1132 were once part of small, compact groups that formed early in the universe's history. These groups experienced rapid early mergers, driven by gravitational attraction and dense local environments. Over time, the largest galaxies coalesced, and one central galaxy, in this case, NGC 1132, emerged as the dominant survivor. With few external galaxies falling in afterward, the group entered its fossil phase. The hot gas, expelled during the merging process, remained as a thermal echo. The stars of the consumed galaxies became part of the growing elliptical, and the system, having exhausted its fuel and its rivals, faded into quiescence. The result was a structure that defied simple classification. NGC 1132 is technically a galaxy, but behaves gravitationally like a group. It possesses the X-ray characteristics of a galaxy cluster, but without the accompanying galactic population. It is massive, luminous, and yet, lonely. Even the dark matter halo of NGC 1132 appears anomalous. Studies using gravitational lensing and dynamical mass modeling suggest that its dark matter distribution is consistent with a full-fledged galaxy group. In other words, NGC 1132 is not merely pretending to be large, it is large, in terms of gravitational mass and energy. It's just that the luminous matter, the stars and galaxies we can see, have collapsed into a single object. The dark skeleton of the group still lingers, invisible but present. There are signs, too, that this loneliness is permanent. Without new galaxies falling in, and without internal gas to reignite star formation, NGC 1132's fate is sealed. It will continue to age. Its stars will grow redder and dimmer. The hot gas may slowly cool over unimaginably long timescales, but it will not form new stars. The system has already entered its twilight, a cosmic quiet that may last longer than the universe's remaining lifespan. And in its silence, NGC 1132 speaks volumes. It tells the story of a group that burned bright and fast, of galaxies that collided and merged, of stars that once formed in bursts and now drift quietly. It shows us what becomes of a galactic society after its age of expansion ends, a single survivor floating through the dark, surrounded by the glowing ashes of its past. Among fossil groups, NGC 1132 is a beacon. Not a beacon of light, but of understanding. It illuminates a pathway that many galaxy groups may one day follow. And in doing so, it reminds us that even in the universe, where change is constant, and collisions are common, There are places where everything has already happened. Nothing more will come. Nothing new will grow. Only the memory remains. There's a strange, almost poetic tragedy in the structure of a fossil group's central galaxy, a colossal elliptical entity formed not by steady growth, but by cosmic violence followed by enduring silence. These lonely giants are among the most massive galaxies in the observable universe, and yet they sit in solitude, surrounded by little more than the lingering heat of ancient mergers and a handful of dim satellites. They are the final form of galactic consumption, the ultimate victor in a long process of gravitational conquest. And in their size, their shape, and their structure, they carry the scars and stories of the galaxies they absorbed along the way. What sets these central elliptical galaxies apart is not just their isolation, but their extraordinary mass and scale. They are often significantly larger and more luminous than typical elliptical galaxies found in active groups or clusters. This is not the product of gradual accretion or simple aging, it's the cumulative result of multiple major and minor mergers over billions of years. Each galaxy that spiraled inward and collided with the center left behind its stars, its dark matter, and sometimes its supermassive black hole. The central elliptical is, in essence, a graveyard, a layered composite of once independent systems now reduced to a single, enormous body. In most large galaxy clusters, there may be 2 or 3 comparably massive galaxies competing for dominance. In fossil groups, that competition ended long ago. The central galaxy is not just the brightest, it is overwhelmingly dominant, often outshining the next brightest galaxy by a factor of 10 or more. This dramatic brightness gap is not arbitrary. It's a direct consequence of its violent history. Over time, gravitational interactions, particularly dynamical friction, pulled the most massive galaxies into the group's center, where they merged with the central elliptical. What remained was a single galactic monolith with few peers and no challengers. These giants often have diffuse outer halos that extend far beyond what we see in typical ellipticals. When observed with sensitive instruments, especially in deep optical or near-infrared imaging, these halos reveal faint features, ripples, shells, or tidal streams. These are the fossilized remnants of past mergers, low-contrast traces of the gravitational chaos that once took place. Each one tells a fragment of the central galaxy's story, a story of satellites cannibalized, of stellar orbits restructured, of interstellar gas shocked, heated, and dispersed. And yet, for all their mass, these giants are often dead in the star-forming sense. Their colors are red, dominated by older, cooler stars. Spectroscopic studies of their stellar populations show that most of their stars are over 8 to 10 billion years old, indicating that star formation ceased long ago. The massive reservoirs of gas that once flowed into the galaxy during mergers have been heated or ejected, and the environment now lacks the cold molecular hydrogen necessary to birth new stars. These galaxies are not just large, they are cosmically ancient, living in the embers of their own past. In terms of morphology, they are often featureless ellipsids, smooth, spheroidal structures without the spiral arms, bars, or dust lanes typical of galaxies still forming stars. Their light profiles follow the de Vauquelins law, a distribution typical of galaxies whose stars have been redistributed by violent relaxation, the gravitational smoothing that occurs during and after mergers. Their cores are dense and massive, often exhibiting high central velocity dispersions, a measure of how quickly stars move in the crowded gravitational environment of the galactic center. These velocity measurements hint at another powerful feature: supermassive black holes. The central galaxies of fossil groups are prime candidates for harboring enormous black holes, far exceeding the mass of the one in our own Milky Way. Some may weigh in at billions of solar masses, grown by the repeated ingestion of black holes from merged galaxies. Occasionally, jets of radio emission or X-ray cavities suggest that these black holes were once active, igniting as quasars or radio galaxies in the past. But like the galaxy itself, many now appear dormant, starved of fuel and asleep. The growth of these lonely giants isn't purely stellar. They also sit at the center of vast dark matter halos, often retaining the full gravitational signature of the original galaxy group. Even though the visible galaxies have disappeared into the central core or drifted too far to contribute significantly to the group's profile, the dark matter remains dense, massive, and invisible. These halos help trap the hot X-ray gas, maintain the group's equilibrium, and slow the escape of energy from the system. But perhaps the most intriguing aspect of these central galaxies is their emotional resonance, the quiet sense of finality they embody. They are the last witness to a once crowded galactic gathering. The group that formed them is no longer active. Its stories have all been absorbed. Its interactions have ceased. And now, this single galaxy floats in a field of hot gas and memory, surrounded by the stretched-out orbits of a few dim companions. In many ways, they are the cosmic equivalent of ancient ruins, monumental, isolated, built from the remnants of what came before. They reflect not just gravitational power, but evolutionary inevitability. Every group that avoids external infall, that merges its members rapidly, and that loses the ability to form new stars, may one day become a fossil group centered on a galaxy like this. As telescopes grow more sensitive and simulations grow more complex, astronomers continue to refine their understanding of these lonely giants. But already, we know enough to say this: they are not anomalies. They are endpoints. They are what happens when a galaxy group grows old, when it merges, consumes, and settles into silence. These massive ellipticals are not simply larger versions of familiar galaxies. They are conclusions, massive, quiet monuments to an era of cosmic violence and transformation. In their stillness, they whisper of everything they've seen, everything they've consumed, and everything that now lies quiet beneath their stars. Surrounding the lonely giant at the heart of a fossil galaxy group is a halo of invisible fire, an ocean of hot gas glowing silently in X-rays, unseen to human eyes but blazing with clues about the group's distant past. This gas, often reaching temperatures of tens of millions of degrees Kelvin, is not just a byproduct of old violence. It is a storyteller. The temperature, composition, and distribution of this gas offer a remarkably detailed autopsy of the galaxy group's history, a layered forensic report from the deep time of cosmic evolution. This intragroup medium, as it's known, is one of the defining features of a fossil group. While the optical light shows a dominant elliptical galaxy surrounded by very few bright companions, the X-ray image tells a different tale, one of lingering heat, shocked plasma, and chemical enrichment. To the trained eye, it's not empty at all. It's full of information. First, the temperature of this gas is critical. In fossil groups, it typically ranges from 10 to 100 million Kelvin, hot enough to prevent it from condensing into stars, but not so hot that it escapes the group's gravitational grip. This gas was heated long ago by merger shocks, the intense gravitational and kinetic energy released when galaxies collided and passed through one another during the group's formative epoch. When those collisions happened, they didn't just tear apart the galaxies, they also stirred and compressed the surrounding gas, heating it up to extreme temperatures. The fossil group's hot gas has remained at these elevated temperatures ever since, largely because there are no more significant events, no new mergers, no fresh infall, to disturb or cool it. It's in a state of quasi-equilibrium, held in place by the gravity of the group's dark matter halo. That stable temperature tells astronomers that the group has been dynamically quiet for billions of years. No recent disturbances. No recent galaxy interactions. Just a long, slow decline into thermal stillness. But it's not just temperature that matters, it's composition too. Embedded in this hot gas are metals, not in the industrial sense, but in the astronomical one. To astronomers, metals refer to any elements heavier than helium, and they are forged inside stars and spread into space by supernovae. The presence of iron, silicon, oxygen, and other elements in the X-ray emitting gas tells us that the stars which once populated this group lived, died, and enriched the intergalactic medium through explosive events. Over time, the accumulation of these elements allows astronomers to estimate not just how old the system is, but how many stellar generations it has undergone. Fossil groups often exhibit high metallicity in their gas, suggesting a long and rich history of stellar evolution. Many stars were born, lived out their lives, and exploded, dumping their enriched guts into the surrounding space. These metals didn't just come from the central galaxy, but also from the dozens of galaxies that once filled the group before being cannibalized. By examining abundance ratios, such as the ratio of iron to alpha elements like oxygen and magnesium, astronomers can even distinguish between different types of supernovae. Type I supernovae, from white dwarfs, and Type II supernovae, from massive stars, produce different chemical signatures. Fossil groups often show a dominance of Type I products, consistent with an aging stellar population that has long since passed its star-forming peak. It's as if the chemical fingerprint of the gas is whispering, "This group has been old for a long time." Then there is the spatial distribution of the gas, its shape, its symmetry, its density profile. In fossil groups, this gas tends to be smooth and spherically symmetric, which is rare among galaxy clusters or younger groups. In active systems, recent mergers and galaxy movements stir the gas, creating asymmetries, clumps, and temperature fluctuations. But fossil groups lack these disturbances. The gas has had time, billions of years, to settle into a relaxed, uniform configuration. This smoothness provides strong evidence that fossil groups are among the most dynamically relaxed systems in the cosmos. They are not being perturbed by external forces. They are not undergoing infall or new growth. They are, in a sense, finished. The hot gas lies like a calm sea, unmoved by storms. The radial profile of the gas, how it changes from the center to the outskirts, can also reveal secrets. In fossil groups, the gas density often follows a steep decline with distance, but remains detectable far from the central galaxy. This shows that the group's dark matter halo is massive and extended, capable of binding gas over wide regions. Despite appearances, the gravitational skeleton of the original galaxy group still exists. It's just that the luminous members have merged into one. In some fossil groups, astronomers observe small temperature dips near the core, possibly the remnants of cooling flows, slow processes where gas cools and flows inward toward the central galaxy. But these flows rarely lead to new star formation in fossil systems. Why? Because the surrounding gas is still too hot, and feedback from past AGN activity likely reheated any cooling material. It's a delicate balance, and one that fossil groups maintain with eerie stability. Interestingly, the entropy profile, a measure of the gas's disorder and thermal energy, can also show that fossil groups formed earlier than other systems of comparable mass. Low entropy in the core often points to early formation and long periods without major heating events. This supports the idea that fossil groups are not just quiet now, they've been quiet for a long time. And finally, the presence of X-ray cavities or bubbles in some fossil groups offers a glimpse into past activity from the central galaxy's supermassive black hole. These cavities, regions where gas has been pushed aside, are likely the leftovers from past AGN outbursts, now faded but still etched into the structure of the group. Even in silence, the past remains visible. In all these ways, from heat to metal to structure, the hot gas enveloping fossil groups is a narrative medium. It records the rise and fall of stars, the violence of ancient mergers, the settling of mass, and the end of motion. It is the medium through which the group remembers its youth, and the lens through which astronomers can read its biography. If galaxies are the bones of a group, the hot gas is its memory, diffuse, glowing, whispering through space. I remember when we were many. I remember the heat, the fire, the collisions. And now I am calm. Fossil galaxy groups, with their eerie silence and dominant central giants, seem rare at first glance, ghostly outliers in the bustling universe. But the deeper astronomers look, the more this apparent rarity begins to shift. It raises a provocative question: are fossil groups genuinely scarce, or are they simply hidden in plain sight, waiting to be properly recognized? At face value, fossil groups account for a modest fraction of all known galaxy systems. As of now, astronomers have positively identified a few hundred fossil group candidates, with several dozen studied in significant detail. Compared to the tens of thousands of known galaxy clusters and groups catalogued by large sky surveys, this number seems vanishingly small. But that's only the tip of the observational iceberg. One major reason fossil groups seem rare is observational bias. Identifying them requires very specific data across multiple wavelengths, especially X-ray observations, which are not always available for every galaxy group. Optical surveys alone don't tell the full story. A massive elliptical galaxy might look solitary in visible light, but without a deep X-ray image to reveal its surrounding hot halo, its status as a fossil group remains ambiguous. Many such systems are simply filed away as isolated ellipticals and overlooked. Moreover, fossil groups are defined not just by their appearance, but by a brightness gap, a requirement that the central galaxy outshines the next brightest member by at least 2 magnitudes. This gap is difficult to establish without sensitive measurements of faint companion galaxies, especially at larger distances. Many fossil groups could be hiding behind incomplete or shallow data. When astronomers began to systematically combine X-ray catalogs like those from Chandra and XMM Newton with optical surveys like the Sloan Digital Sky Survey (SDSS), they started uncovering more of these systems. The realization dawned that fossil groups might not be rare at all, just under-recognized due to their misleading simplicity and the need for multifaceted analysis. In fact, some studies suggest that 10% to 20% of all galaxy groups in the local universe might be fossil systems, or well on their way to becoming one. This is a staggering estimate, suggesting that fossilization is not a rare evolutionary accident, but a common endpoint in the lives of many galaxy groups. Once a group experiences rapid early formation and fails to acquire new members through infall, it is likely to settle into a fossil phase. Computer simulations reinforce this possibility. Cosmological models that trace dark matter halos and baryonic physics over billions of years routinely produce fossil groups as a natural byproduct of hierarchical structure formation. Groups that form early in high-density regions, and then find themselves in underdense environments later, tend to fossilize, growing quiet as external gas and galaxies stop falling in. Interestingly, the fossil phase may not be a permanent identity. Some simulations propose that groups can transition in and out of this state. A fossil group today might accrete a few large galaxies in a billion years, temporarily losing its status before re-entering the fossil phase later. This dynamic possibility implies that what we see as a fossil group is just a snapshot in time, a moment of quiet in a system's otherwise active evolution. Another complication is the redshift dependency of fossil group detection. At higher redshifts, meaning farther back in time, it becomes more difficult to resolve faint galaxies and X-ray halos. This limits our ability to identify fossil groups in the early universe, even though simulations suggest they should exist. In fact, fossil groups at high redshift would provide some of the most powerful evidence for early, rapid structure formation, if we can find them. Furthermore, there may be a whole spectrum of fossil systems that we haven't yet fully classified. Some groups may be only partially fossilized, central galaxies that have absorbed most, but not all, of their companions. Others might be fossil clusters, large-scale analogues of fossil groups with hundreds of galaxies collapsed into a few massive ones. These systems may fall outside our current classification schemes, even though they follow the same evolutionary logic. Even within the fossil group population, there are degrees of complexity. Some fossil groups show signs of recent AGN activity or faint substructure in their hot gas halos, hinting at minor internal processes still at work. Others are pristine, perfectly symmetric in X-ray, with no visible disturbances, quiet for billions of years. This diversity makes it harder to pin down fossil groups with a single diagnostic tool. And then there's the philosophical question: how rare is rare in the universe? When you're dealing with structures on scales of millions of light years and lifetimes measured in billions of years, even a rare system might number in the thousands, far more than we could ever study in detail. Fossil groups might be rare in a statistical sense but still common enough to play a vital role in our understanding of galaxy evolution. So what we're left with is a tantalizing duality. Fossil groups are both rare and common. Rare in that they represent a quiet, terminal phase of group evolution. Common in that many groups may pass through this phase, however briefly or imperceptibly. Their scarcity is a function of detection limits, not necessarily cosmic distribution. In the end, the universe may be littered with the remains of once crowded groups, ancient galactic graveyards hidden behind our observational limitations. And every time we peer deeper, with better instruments and broader sky coverage, we find more of them waiting in the dark. They may not announce themselves with explosive brightness or sweeping arcs of spiral arms. But they are there, glowing faintly in X-rays, whispering their fossilized stories from across the cosmos. Fossil galaxy groups, quiet as they may seem, are not just isolated curiosities floating on the cosmic sea. They are woven into the very fabric of the universe's large-scale structure. Their existence tells us more than just how galaxies evolve. It speaks to the timing and geography of cosmic history itself. These ancient, settled systems are cosmic footprints left behind by an era of rapid structure formation, possibly among the earliest signs of galaxy groups coalescing in the densest parts of the young universe. In this way, fossil groups are not just the end state of galaxy evolution, they are also clues to its beginning. To understand their cosmological implications, we have to step back and consider the hierarchical model of structure formation, the idea that the universe builds its large-scale architecture from the bottom up. Tiny fluctuations in the density of matter in the early universe, seeded during inflation, gradually grew under the influence of gravity. Over billions of years, small clumps of dark matter merged into larger halos, drawing in gas and forming stars, galaxies, groups, and eventually massive clusters. In this hierarchical model, galaxy groups are expected to be the intermediate phase between isolated galaxies and full-blown clusters. They form earlier than massive clusters because they involve less matter and less gravitational collapse time. But fossil groups defy even that expected pace. They appear to have formed especially early, and they settled especially quickly. The galaxies in these systems didn't wait around for a leisurely accretion of companions. They collapsed fast, merged rapidly, and evolved into a quiet state while the rest of the universe was still bustling with assembly. This means that fossil groups might be some of the first stable galactic structures to emerge after the universe cooled enough to form stars. Their early formation is supported by their old stellar populations, high metallicities, and the relaxed, symmetric state of their X-ray gas halos. These are all signatures of a system that had a head start, a system that formed in a dense region of the early universe, where matter clumped more quickly and collapsed more efficiently than in average environments. Such regions are not evenly distributed. The cosmic web, the large-scale structure of the universe, consists of filaments, nodes, and voids. Galaxies and groups form preferentially along filaments, especially at the intersections where gravitational influence is strongest. Fossil groups are likely to have emerged in these intersections, cosmic knots where early overdensities led to rapid gravitational collapse. Their spatial distribution may hold clues about the geography of ancient structure. If fossil groups are found in statistically significant numbers along certain filaments, or in particular environments, this could help refine our models of early density perturbations and the shape of the dark matter scaffolding that guided structure formation. In this sense, fossil groups serve as signposts of early gravitational activity, fossilized echoes of the universe's first attempts to organize matter on large scales. Furthermore, because fossil groups appear to have avoided significant late time infall, they offer a kind of closed system snapshot of what the universe looked like billions of years ago. Most galaxy clusters are constantly ingesting new material. Smaller groups, gas clouds, and individual galaxies still fall into them, making it hard to disentangle their past from their present. Fossil groups, by contrast, represent a sort of cosmic time capsule, a system that formed early and has remained largely untouched. This makes them especially valuable for cosmological models. By comparing fossil groups at various distances, and thus at various points in time, astronomers can track the evolutionary history of dark matter halos, hot gas, and galaxy populations without the complications of ongoing growth. In a way, fossil groups let us isolate time itself as a variable. There's also a deeper implication. If fossil groups are more common at higher redshifts, this supports the idea that they formed during the universe's cosmic noon, a period about 8 to 10 billion years ago, when star formation and galaxy mergers peaked. Systems that rapidly collapsed and merged during this time may have already fossilized by the present day. This challenges the assumption that fossil groups are simply the result of slow isolation in the outskirts of the universe. Instead, they may be the oldest survivors of a more violent, active era, the early overachievers in the Great Cosmic Assembly. Additionally, fossil groups may be key to understanding baryonic feedback mechanisms on cosmological scales. Their smooth X-ray halos and old stellar populations suggest that the feedback from active galactic nuclei, AGN, supernovae, and merger-driven shocks was particularly effective in heating and expelling gas early in the system's history. The result is a structure where star formation has been suppressed for billions of years, and understanding this process can help refine simulations of galaxy formation across the universe. Fossil groups also tie into dark energy and cosmic acceleration. Because they represent early forming, relaxed systems, they provide a benchmark against which to measure the growth rate of cosmic structure. By comparing the observed number and distribution of fossil groups to predictions from different cosmological models, astronomers can test the behavior of dark energy over time. If the universe's expansion had been slower or faster, or if the dark energy density had evolved differently, the number and characteristics of fossil groups would change. In this way, these quiet structures help constrain the dynamics of the universe itself. Perhaps most intriguingly, fossil groups point toward a possible future for many of today's galaxy groups and clusters. As the universe continues to expand, large-scale structure formation will eventually grind to a halt. New material will stop falling into clusters. Star formation will cease. Galaxies will merge into ever larger ellipticals. In time, many systems may become fossilized, their members absorbed, their fuel exhausted, their heat lingering in halos of X-ray gas. The universe, once filled with luminous spirals and active mergers, may slowly become a landscape of fossil groups, each one a cosmic relic, silent and alone, floating in an ever darker sky. Fossil groups are not just fossils of the past. They are harbingers of the universe's ultimate destiny. They remind us that the grand process of structure formation, as immense and dynamic as it once was, will one day give way to stillness, and in that stillness, to a new kind of beauty, the beauty of cosmic memory, preserved in silence. At first glance, fossil galaxy groups might seem like just another variety within the great zoo of galactic structures, a quieter sibling of typical galaxy groups or smaller cousins of massive clusters. But when we place them side by side with more familiar galactic ecosystems, their strange uniqueness becomes clear. These are not simply groups that have aged gracefully. They are radically altered survivors, products of accelerated evolution and extreme isolation. To understand their significance, we need to compare them in detail to their more common relatives: regular galaxy groups, galaxy clusters, and compact groups. Let's begin with regular galaxy groups, the most common type of galactic environment in the nearby universe. These typically consist of anywhere from a few to a few dozen galaxies bound together by mutual gravitational attraction. The Milky Way and Andromeda, for example, are part of the local group, a small collection of galaxies that also includes the large and small Magellanic Clouds, M33, and dozens of dwarf galaxies. In these groups, while interactions do occur, they are often gradual and intermittent. Star formation continues. Gas flows between galaxies. No one galaxy dominates to an extreme degree. The group remains dynamically alive, a constantly shifting network of mutual interactions, accretion, and growth. In contrast, a fossil group has undergone something entirely different. It started much like a regular group but then rapidly collapsed and merged its members. The dominant galaxy at its center has absorbed most of the brightest companions, leaving behind only faint dwarfs and a cloud of hot, X-ray emitting gas. The energy of past collisions lingers in that gas, but the galaxies themselves have largely disappeared, consumed by the central giant. What remains is dynamically quiet, with little star formation, few interactions, and an eerie stability that belies the violent chaos of its past. Then there are galaxy clusters, larger, richer, and more massive than any group. These contain hundreds or even thousands of galaxies, often arranged around a central cluster core. Unlike fossil groups, galaxy clusters remain highly active environments. Galaxies within clusters experience strong gravitational tides, frequent high-speed encounters, and environmental effects like ram pressure stripping, where the hot intracluster medium tears away their gas as they move through it. Star formation is often suppressed in cluster galaxies, but not because they've merged into one. Rather, they're being strangled by the dense environment. And while central dominant galaxies exist in clusters, the so-called brightest cluster galaxies, BCGs, they rarely account for such a large fraction of the total luminosity as in a fossil group. Clusters are still growing, still evolving. They are crowded and chaotic, full of galaxies and gas in motion. Fossil groups stand apart in both their structure and their history. They possess X-ray halos as large and bright as small clusters, but without the accompanying population of luminous galaxies. Their dark matter halos suggest they are group-sized in mass, but cluster-like in thermal energy. Their central galaxies are often more massive than even some BCGs, an indication of how thoroughly they have cannibalized their peers. And unlike clusters, which continue to pull in new material from the cosmic web, fossil groups have largely stopped growing. They are frozen, not just in terms of merger activity, but in terms of their entire developmental path. Now consider compact groups, like Hickson Compact Group 92, systems where a small number of galaxies are packed tightly together, often within a volume only a few times the size of a single galaxy. These are highly interactive environments, full of tidal tails, distortions, and mergers in progress. They're dynamic, turbulent, and short-lived on cosmological timescales. Compact groups are thought to evolve rapidly, with member galaxies merging into a single elliptical within a few billion years, potentially forming the precursor of a fossil group. In this sense, compact groups may represent an earlier stage in the fossil group life cycle. However, fossil groups differ in a key way. They've already passed through that compact, violent phase. They've emerged on the other side as settled, spherical, and symmetrical. While compact groups are like families in conflict, fossil groups are like solitary elders, the result of that conflict, now aged and alone. Where compact groups show obvious signs of interaction, fossil groups are smooth and relaxed, having had enough time to erase their scars. Another key differentiator is luminosity gap, the brightness difference between the central galaxy and its brightest remaining companion. In fossil groups, this gap is at least 2 magnitudes, meaning the central galaxy is more than 6 times brighter than any other. This is rarely seen in regular groups, clusters, or compact groups. It's not just a statistic, it's a signature of near-total consumption. And then there's the hot gas component. Regular groups often have modest X-ray halos, or none at all. Compact groups may have warm gas, but not necessarily in large quantities. Galaxy clusters have extensive, hot intracluster media, but they also have many galaxies to match. Fossil groups are unique in having X-ray halos that are disproportionately bright relative to the visible population of galaxies. This X-ray excess is a key tool in their identification, a ghostly glow of past violence now radiating steadily through space. Even in terms of star formation, the differences are stark. Galaxies in regular groups and compact systems often still have gas and are forming stars. In fossil groups, star formation is effectively quenched. The central elliptical galaxy is dominated by old, red stars, and there's little cold gas left to trigger new bursts of creation. The system has entered a thermally passive phase, maintained by the heat of its own ancient activity. In summary, the contrast is profound. Fossil groups are like burnout cities, where the towering central skyscraper stands alone, surrounded by ruins and heat from a fire long extinguished. Regular groups are like small towns, full of interaction and potential. Clusters are crowded metropolises, still bustling with activity. Compact groups are flashing powder kegs, waiting to go off. Fossil groups are what remains after the flash. After the bustle. After the mergers, after the chaos, after the fire. They are what is left when the story ends, and the universe turns the page. In the pursuit of understanding fossil galaxy groups, astronomers and astrophysicists have turned to one of the most powerful tools in their arsenal: cosmological simulations. While telescopes allow us to look outward into space and backward in time, simulations let us create entire universes in silico. Sandbox models where gravity, gas, dark matter, and time itself are all programmable. These virtual universes are not science fiction. They are built on physics, coded in algorithms, and capable of reproducing the immense complexity of structure formation. And when it comes to fossil groups, simulations have proven especially illuminating, offering a controlled environment to explore how these ghostly systems form, evolve, and settle into silence. At the heart of these simulations are the laws of gravity and hydrodynamics, operating over cosmological timeframes. Large-scale simulations, like the Millennium Simulation, Illustris, Eagle, and TNG, the next generation, model the evolution of the universe from its infancy, just after the Big Bang, to the present day. They track how tiny quantum fluctuations in the early universe evolve into galaxies, groups, and clusters. But more importantly for our purposes, these simulations allow researchers to identify systems that evolve into fossil groups naturally, without forcing them into the model artificially. One of the key discoveries from these simulations is that fossil groups arise organically in the timeline of hierarchical structure formation. They are not anomalies or the result of unusual starting conditions. Rather, they emerge when certain galaxy groups experience early, rapid formation, followed by a long period of isolation. This finding is crucial because it confirms that fossil groups aren't just artifacts of our observations. They're a real and expected outcome of cosmic evolution under standard cosmological models like lambda-CDM. In the simulated universe, you can watch it happen. Small dark matter halos merge to form larger ones, gas collapses into galaxies. Those galaxies fall toward one another, and over a few billion years, a single massive elliptical galaxy forms at the center. As the simulation progresses, the group consumes its brightest members, heating its gas and building a large X-ray halo. The system stops accreting new galaxies, either because it's in a low-density region or because there simply aren't any more to draw in. The simulated fossil group then quietly coasts through the rest of cosmic time, just as we observe in real X-ray and optical surveys. These digital fossils match real observations in striking ways. Their central galaxies dominate the luminosity profile, often outshining the next brightest galaxy by 2 magnitudes or more. Their X-ray halos remain hot and extended, matching Chandra and XM Newton measurements. Their stellar populations grow old, and their merger activity halts. In both the virtual universe and our actual one, these systems are cosmic quiet zones, relics of once violent activity now preserved in thermal equilibrium. One major advantage of simulations is the ability to control variables that are impossible to manipulate in the real universe. Researchers can tweak initial density fields, dark matter distributions, merger rates, gas cooling functions, star formation efficiencies, and AGN feedback prescriptions. By doing so, they can test how sensitive fossil group formation is to different environmental and internal conditions. For example, simulations have shown that strong AGN feedback, energy released from accreting black holes, plays a crucial role in halting star formation and maintaining the hot gas halo. Without it, gas might cool and form stars, keeping the system alive, instead of letting it fossilize. Another powerful insight from simulations is the importance of merger timing. Fossil groups tend to form when a group assembles its mass earlier than average, often before redshift z is almost equal to 1, or about 7 to 8 billion years ago. The earlier these mergers occur, the more time the group has to relax and for its gas to settle into a stable X-ray halo. Late mergers, on the other hand, tend to disrupt this process and prevent fossilization. This correlation between formation time and fossil status is now one of the core findings replicated across multiple simulation projects. Simulations also help clarify the dynamical stability of fossil groups. By tracking the orbital decay of satellite galaxies due to dynamical friction, simulations demonstrate how and why the brightest members spiral inward and merge with the central elliptical. They even replicate the circularization of these orbits and the gradual smoothing of the group's overall structure, exactly as we observe in the symmetric X-ray profiles of actual fossil groups. These virtual galaxies don't just look like fossils. They behave like fossils, undergoing the same processes we infer from real-world observations. Interestingly, simulations also suggest that fossil groups may not be permanently fossilized. If, by chance, new galaxies fall into the system, say, from a neighboring filament, the system could exit the fossil phase and appear more like a standard group again. This dynamic behavior adds nuance to our understanding. Fossil groups are not necessarily terminal endpoints. They are states of balance, and that balance can shift with the arrival of new material. This insight helps explain why some groups seem to straddle the line between fossil and non-fossil status. Their identities are not binary, but fluid across cosmic time. Furthermore, simulations help test the mass-luminosity relationship and the role of dark matter halos. Fossil groups, despite their small number of visible galaxies, often occupy surprisingly massive halos, comparable in some cases to clusters. This decoupling of visible mass and total gravitational mass is clearer in simulations, where every particle of dark matter can be tracked directly. The result is a more precise mapping between observable properties and the invisible structure that binds the system together. Even more detailed simulations, so-called zoom-in simulations, focus on individual fossil groups at ultra-high resolution. These models allow researchers to track the evolution of individual stars, black holes, and gas clouds within the group, capturing the fine structure of the central galaxy and the thermal dynamics of its X-ray halo. These simulations show, for instance, how AGN outbursts can carve cavities into the hot gas, how star formation shuts down, and how gas metallicity spreads across the group. Every nuance deepens our understanding and helps explain what we see in real fossil systems. Ultimately, simulations serve as both a mirror and a microscope. They mirror the observed universe, proving that fossil groups are a natural outcome of standard physics. And they magnify hidden mechanisms, revealing the forces and flows we can't yet observe directly. With each new generation of simulations, aided by machine learning, faster processors, and more sophisticated physics, our picture of fossil groups sharpens. In a sense, these simulations are fossils themselves, digital records of how structure might evolve under different cosmic conditions. They allow us to rewind time, fast-forward development, and replay the evolution of galaxy groups over and over again, each time learning something new about the quiet giants that sit at the end of the universe's galactic life cycle. The concept of fossil galaxy groups is already a compelling chapter in the story of cosmic evolution, ancient systems dominated by a single, massive galaxy, surrounded by the glowing remains of long-past galactic mergers. But the universe rarely stops at one scale. As astronomers continued to probe the depths of space, a provocative question emerged. If fossil groups exist, could there be even larger structures that follow the same evolutionary trajectory? The answer appears to be yes. Enter the fossil clusters, the enormous, rarer, and perhaps even more mysterious bigger cousins of fossil galaxy groups. Fossil clusters follow the same basic principle as their smaller counterparts: a dominant central galaxy, a dearth of comparably bright neighboring galaxies, and an extended halo of hot, X-ray emitting gas. But the scale is much grander. Where fossil groups are typically the result of a few dozen galaxies merging into one, fossil clusters may originate from hundreds or even thousands of galaxies, forming massive structures that stretch across millions of light years. These are not just galactic ghosts, they are the fossilized bones of cosmic giants. To qualify as a fossil cluster, the system must exhibit the same optical magnitude gap used to define fossil groups, a difference of at least 2 magnitudes between the brightest galaxy and the next brightest companion within half the virial radius. In other words, the central galaxy must outshine all others in its neighborhood by a factor of 6 or more. This is a striking feature in any context, but in a galaxy cluster, where competition is fierce and galaxy populations are dense, it's extraordinarily unusual. It suggests that the central galaxy in a fossil cluster has managed to outgrow and outlast all competition, becoming a colossal elliptical entity at the heart of a nearly empty realm. Such central galaxies are often brightest cluster galaxies, BCGs, but in fossil clusters, they appear supercharged, overgrown, even by BCG standards. These are behemoths, sometimes over 1,000,000 light-years in diameter, filled with old stars and harboring central supermassive black holes of unimaginable mass. Their sizes and brightnesses alone imply an evolutionary history soaked in mergers. They are the ultimate products of galactic cannibalism on a titanic scale. But what makes fossil clusters particularly fascinating is the surrounding environment, or more accurately, the lack of one. In most galaxy clusters, even with a dominant central galaxy, there are still dozens or hundreds of large galaxies nearby, forming a lively community of interactions, orbits, and infalls. In fossil clusters, that vitality is gone. There are faint galaxies, yes, dwarfs, satellites, and debris, but the major players are missing. The brightest companions have already been consumed. The cosmic feasting is complete. One of the best-known candidates for a fossil cluster is RxJ 1416.4 plus 2315, an X-ray bright system with properties eerily similar to both galaxy clusters and fossil groups. It displays a massive central elliptical galaxy surrounded by an X-ray halo stretching hundreds of kiloparsecs, and yet it lacks any comparable galactic neighbors. Observations show it to be gravitationally massive, easily within cluster territory, but optically underpopulated at the bright end of the luminosity function. It's as if a typical cluster had all its brightest members suddenly vanish, leaving behind only one luminous survivor and a crowd of faint shadows. This mismatch between gravitational mass and galaxy population is key to identifying fossil clusters. Like fossil groups, they can be deceptive in optical surveys, appearing at first glance as isolated giants. Only when their deep X-ray halos are revealed, or their dark matter masses are estimated via gravitational lensing or galaxy velocity dispersion, do their true natures come into focus. They are massive halos with little visible company, lonely monarchs ruling over vast, quiet kingdoms. The existence of fossil clusters challenges certain assumptions in structure formation theory. Standard cosmological models predict that clusters should continue accreting material from the cosmic web well into the present epoch. But fossil clusters suggest that some massive halos may have finished growing early, effectively becoming closed systems that consumed their last major galactic meal billions of years ago. This implies that fossilization is not confined to small or intermediate scales. It can occur even in the most massive gravitational wells in the universe, under the right conditions. Simulations support this view. High-resolution models show that some galaxy clusters can form especially early in regions of elevated density, rapidly merging their massive galaxies and then falling into long-term isolation. These simulated fossil clusters often develop huge X-ray halos, high central entropies, and stable dark matter distributions. Their histories are front-loaded with action, intense merger phases followed by long, quiet plateaus of gravitational stability. Interestingly, fossil clusters may be precursors to future superclusters. Over the coming billions of years, the universe's expansion will isolate gravitationally bound systems from one another. Clusters that have already fossilized may remain self-contained islands as other nearby structures drift beyond the cosmological horizon. In this sense, fossil clusters could become the final gravitational oases in an otherwise dark and expanding universe, the last congregations of matter in a cosmos growing colder and more diffuse. But the rarity of confirmed fossil clusters raises compelling questions. Are they inherently uncommon, or have they simply been underobserved due to the limitations of our detection methods? Their hybrid nature, visually sparse like groups, but gravitationally rich like clusters, makes them hard to classify using traditional optical surveys. Many may be hiding in plain sight, waiting for deeper multi-wavelength surveys and more sensitive X-ray observations to bring them to light. In the coming years, missions like eROSITA and telescopes like JWST and the Vera-C Rubin Observatory will deepen our view of the cosmic landscape. They may reveal that fossil clusters are not rare relics but a natural, if undercounted, endpoint of galactic evolution on the grandest scale. With improved simulations, we'll be able to model their formation more precisely, tracing the paths of galaxies that, in some corners of the universe, merged early, settled fast, and became eternal giants in an ocean of silence. Ultimately, fossil clusters expand the scope of the fossil phenomenon from small group environments to the cosmic metropolis. They are a sobering reminder that even the busiest galactic cities may one day fall quiet, not through catastrophe, but through consumption, exhaustion, and the simple passage of time. Fossil galaxy groups may appear deceptively quiet in optical images, serene systems with a single luminous galaxy and little else. But beneath that tranquil appearance lies a rich, invisible landscape. One of the most profound ways fossil groups contribute to our understanding of the universe is by offering a window into the distribution of dark matter. Since the visible matter in these systems has been largely consumed or absorbed, what remains is an unusually clean laboratory to study the gravitational skeleton that binds everything together. Dark matter, though invisible, reveals itself through its gravitational influence. Galaxies orbit within dark matter halos, and the gas that permeates groups and clusters is heated and confined by the gravitational potential wells those halos create. In fossil groups, where the usual optical distractions of multiple competing bright galaxies are gone, we are left with a stripped-down system, a single dominant elliptical galaxy sitting in a halo of hot gas and dark matter. That minimalism is precisely what makes fossil groups such ideal candidates for dark matter research. One of the key methods by which astronomers infer the dark matter distribution in these systems is through the study of their X-ray emitting gas. This hot gas, left over from ancient mergers and compressed by the group's gravity, settles into hydrostatic equilibrium within the gravitational potential well. The temperature, density, and radial profile of this gas can be measured in exquisite detail by X-ray observatories like Chandra and XM Newton. From these measurements, researchers can deduce the total mass profile of the system, not just the mass from stars and gas, but from dark matter as well. Interestingly, fossil groups often exhibit very deep gravitational wells, deeper than one might expect based solely on the visible galaxy content. Despite having few bright galaxies, their gravitational potential is consistent with rich group or even cluster-scale halos. This mismatch between the luminous matter and the total mass confirms that fossil groups are dominated by dark matter. In some cases, the central galaxy alone accounts for only a small fraction of the total gravitational pull, with dark matter comprising the overwhelming bulk. What makes this even more fascinating is how concentrated these dark matter halos appear to be. Observational studies and simulations alike show that fossil groups tend to have higher halo concentration parameters than non-fossil groups of similar mass. That is, their dark matter is more tightly packed toward the center. This fits with the idea that fossil groups formed early in cosmic history. In the standard cosmological model, earlier forming halos tend to be more compact because the universe was denser when they collapsed. This makes fossil groups cosmic time stamps, encoding when their dark matter halos assembled based on their density profiles. Gravitational lensing offers another tool for probing dark matter in fossil groups. While most strong lensing systems are associated with massive clusters, weak gravitational lensing, the subtle distortion of background galaxies due to foreground mass, can also be used to study fossil groups. These analyses, though technically challenging due to the low number of visible galaxies, often reveal mass distributions that exceed expectations based on visible light alone, once again underscoring the dominance of dark matter. Moreover, fossil groups are helpful in calibrating the mass-luminosity relation, a fundamental scaling law in cosmology. In most systems, there is a loose correlation between the total mass, as inferred from gravitational dynamics, and the total optical luminosity, from all the stars in the group. Fossil groups tend to break this pattern. Their optical luminosity is low, thanks to the lack of bright companions, but their total mass remains high. This discrepancy forces astronomers to reevaluate standard assumptions and improve models for how galaxies form and how baryonic matter traces, or fails to trace, the underlying dark matter. Another angle of investigation is the radial distribution of dark matter in fossil systems. Simulations suggest that the halos of fossil groups are not just more concentrated but also more relaxed, meaning the dark matter has settled into a stable, isotropic distribution without significant substructure. This is in contrast to many active groups or clusters, where ongoing mergers and infall can produce clumps, streams, or asymmetries in the dark matter distribution. Fossil groups, by contrast, appear dynamically mature, having had billions of years for any internal irregularities to smooth out. This smoothness makes them excellent for testing theories about dark matter itself. For instance, certain exotic models of dark matter, such as self-interacting dark matter or warm dark matter, predict subtle differences in halo structure compared to standard cold dark matter. Fossil groups, with their clean gravitational environments and well-behaved gas halos, are among the best systems in which to look for these deviations. Any unusual features in their mass profiles could point to new physics. Finally, fossil groups provide insight into the role of dark matter in galaxy evolution. The deep potential wells in these systems not only confine hot gas but also prevent its escape even after it's been heated by supernova explosions or AGN feedback. This helps explain why fossil groups have large, stable X-ray halos and why star formation is quenched so effectively. The dark matter doesn't just shape the group's gravitational field, it governs its entire evolutionary path. In many ways, the dark matter in fossil groups tells a story that the stars no longer can. The visible galaxies have merged and faded. The fireworks of star formation have ended. But the invisible scaffold remains, massive, ancient, and intact. By studying this scaffold, we unlock not just the hidden architecture of a single system, but clues to the very nature of matter and structure in the universe. Fossil groups, then, are more than relics of galactic evolution. They are gravitational fossils, preserving the imprint of the dark matter halos that shaped them, halos that formed in the early universe and settled into silence, their secrets etched into the geometry of space and the temperature of glowing gas. One of the defining features of fossil galaxy groups is their remarkable stillness, not just in terms of galactic motion, but in the absence of something far more fundamental, star formation. These systems are not teeming with bright blue stars, glowing nebulae, or bursts of youthful light. Instead, they are largely dominated by old, red stars, ancient populations that have long since ceased forming. But what causes this stillness? The answer lies in the intense and violent history of galactic interactions and mergers, which leave the surrounding gas too hot, too diffuse, and too hostile for new stars to ignite. In the broader context of galaxy evolution, the availability of cold gas is the key ingredient for star formation. Stars are born when dense regions of cold molecular gas collapse under their own gravity, eventually forming protostars and then full-fledged stars. In spiral galaxies like the Milky Way, these gas reservoirs are regularly replenished by infalling material, either from galactic outskirts or the intergalactic medium. But in fossil groups, that star-forming fuel is largely absent. What happened to it? The answer begins with the very process that created the fossil group in the first place: galaxy mergers. These collisions are not gentle events. As two galaxies spiral into one another, their gas clouds slam together, compress, and heat up. Shocks propagate through the interstellar medium. Gravitational tides tear stars from their orbits, flinging them into long tails. But most critically, the gas within each galaxy is violently stirred and often driven toward the center, triggering intense but brief bursts of star formation, so-called starbursts, followed by a rapid quenching. During these bursts, massive stars form in great numbers. But such stars live fast and die young, ending their lives in supernova explosions that pump enormous amounts of energy back into the surrounding gas. This feedback process heats the gas and can drive much of it out of the galaxy's star-forming regions. The merger-induced starburst essentially uses up and heats up the available cold gas, cutting off the conditions necessary for continued star formation. Now scale this process up to an entire galaxy group. Fossil groups form when many galaxies within a group merge into a single, massive elliptical. This process is not just a series of binary mergers. It's a chain reaction of gravitational violence, where one collision leads to another, each one adding heat and disorder to the system. The result is a large reservoir of hot intergalactic gas, known as the intragroup medium, that remains suspended in the group's deep gravitational well. This gas is X-ray luminous, with temperatures often exceeding tens of millions of degrees Kelvin. At these temperatures, gas particles move too fast to collapse into stars. Instead of clumping into dense clouds, they remain diffuse and thermally stable, emitting their energy as X-rays over hundreds of millions of years. This state of equilibrium is difficult to disturb. The group is left with a vast amount of gas, but it's the wrong kind of gas for making stars. It is hot, ionized, and dilute. No star nursery could survive in such an environment. There's also the role of active galactic nuclei, AGN, feedback, the energetic outbursts from supermassive black holes at the centers of galaxies. The central galaxy in a fossil group often hosts a supermassive black hole that may have experienced powerful accretion phases during or after the mergers. As the black hole feeds on infalling gas, it releases vast quantities of energy in the form of radiation and powerful jets. This feedback acts like a cosmic furnace, further heating the surrounding gas and preventing it from cooling back down. This AGN heating is believed to be a self-regulating process. As gas begins to cool and flow inward, it feeds the black hole, which then releases more energy and halts the inflow. This balance can persist for billions of years, keeping the group quiescent and thermally stable. Without AGN feedback, the gas might cool and reignite star formation. But with it, the fossil group remains locked in dormancy. Another factor contributing to the shutdown is the gravitational stripping of gas from infalling galaxies during earlier merger phases. As satellite galaxies fell into the growing group, they were subjected to ram pressure stripping, the force exerted by moving through the dense intragroup medium. This process can effectively strip gas from a galaxy's disk, halting star formation even before the final merger occurs. The stripped gas, in turn, becomes part of the diffuse hot halo, adding to the reservoir of unusable fuel. It's a perfect storm. Mergers, supernovae, black holes, and thermal pressure all work together to heat the gas, disperse the cold clouds, and create an environment fundamentally hostile to star formation. What remains is a fossil group where new stars are not just unlikely, they are effectively impossible under current conditions. This quenching process also explains the color and brightness of fossil group galaxies. The central elliptical, having exhausted or ejected its cold gas, contains mostly population II stars, older, redder, and metal-rich. The blue hues of young stars are absent. In optical images, fossil groups appear visually muted, their central galaxy glowing in soft gold rather than vibrant blue. Spectroscopic studies confirm the presence of old stellar populations, with ages often exceeding several billion years. This total suppression of star formation over cosmic timescales makes fossil groups not just relics of galactic mergers, but grave sites of starbirth. They are regions where the conditions for creating new stars have been permanently erased by the very processes that formed the group in the first place. It is a paradoxical beauty. The fire of creation burns so hot and so fast that it leaves nothing but silence in its wake. In a universe filled with dynamic star-forming regions, swirling galaxies, and expanding clusters, fossil groups stand as cosmic cenotaphs, memorials to a bygone era of creation, now locked in thermal stillness. Their very existence is a testament to how violence can lead not to chaos, but to a kind of quiet, enduring order, a galaxy group not in the process of becoming, but in the state of having become. In the heart of nearly every massive galaxy lies a gravitational abyss, a supermassive black hole with millions, sometimes billions, of times the mass of our Sun. These black holes are not mere bystanders in galactic evolution. They are powerful engines capable of influencing their entire environment on a galactic, even intergalactic scale. In fossil galaxy groups, where the central galaxy has grown enormous through a long history of mergers, the black hole at its core is likely a true titan, a cosmic monarch with a reach that extends far beyond its event horizon. The role of these black holes in fossil groups is central to understanding why these systems are so quiet, so still, and so thoroughly quenched. They do not act in isolation, nor do they operate constantly. Instead, their influence is episodic but profound, coming in bursts of activity known as AGN, active galactic nucleus feedback, where the black hole feeds on surrounding gas and unleashes energy across the electromagnetic spectrum. Let's first understand how this process works. As gas falls toward the black hole, it forms an accretion disk, heating up as it spirals inward. This gas doesn't fall in silently. It becomes superheated to millions of degrees, emitting intense X-rays and even gamma rays. Jets of plasma can erupt from the poles of the black hole at nearly the speed of light, while winds and radiation blast outward from the accretion region. Though the black hole itself has no voice, its feeding phase is a cosmic roar, sending shockwaves through its surroundings. In fossil groups, where most of the bright satellite galaxies have been consumed, this central black hole becomes the sole active source of high-energy feedback. It interacts not only with the galaxy's interstellar medium but with the vast hot gas halo, the intragroup medium, that stretches far beyond the visible boundaries of the galaxy. This interaction has two primary effects: heating the gas and preventing its cooling. Why is this important? Because cooling is the first step toward forming stars. Hot gas radiates away its energy in the form of X-rays, gradually losing temperature until it condenses and forms dense molecular clouds, the raw material for star birth. In many galactic environments, this cooling process fuels ongoing star formation. But in fossil groups, the black hole acts like a cosmic thermostat, injecting just enough energy to keep the gas hot, extended, and uncondensed. This process is not just theoretical. X-ray observations of fossil groups have revealed cavities or bubbles in the hot gas halo, voids that appear to have been inflated by jets from the central AGN. These bubbles, often detected by telescopes like Chandra, are direct evidence of mechanical feedback. The black hole is not only heating the gas through radiation but physically pushing it aside, disrupting the thermal profile and distributing energy throughout the group. This AGN, maintenance mode, low luminosity, but persistent, may operate for billions of years, preventing cooling flows and keeping the system in a long-term state of thermal balance. In fossil groups, the efficiency of this feedback seems to be especially high. There are several reasons for this. First, the central galaxy is massive and stable, providing a deep gravitational potential that helps trap the heated gas. Second, the lack of galactic disturbances, no new mergers, no infalling galaxies, means there is little to interfere with the feedback loop. The black hole can feed and regulate the system in relative peace, unchallenged by external perturbations. Furthermore, simulations suggest that fossil groups host some of the most massive black holes relative to their host galaxies. This likely results from their rich merger history. Every time two galaxies merged, their central black holes may have coalesced, growing the core black hole in mass and influence. The result is a central engine far more powerful than average, capable of dominating the group's thermodynamics even long after the mergers have ended. Another fascinating implication of black hole feedback in fossil groups is its impact on metallicity gradients. As AGN-driven winds and jets move through the intragroup medium, they carry with them elements produced by supernovae, iron, oxygen, silicon, and more. This enriches the hot gas halo, spreading metals throughout the group and creating chemical fingerprints of past star formation and AGN activity. Observations have shown that some fossil groups possess unusually uniform metallicity profiles, suggesting that their central black holes have played a major role in stirring and mixing the gas. There's also a connection between the black hole's activity and the suppression of cooling flows, a phenomenon expected in massive halos. In the absence of feedback, hot gas should cool rapidly and fall inward, forming stars and feeding the central galaxy. But in fossil groups, this cooling flow is often missing or much weaker than expected. The energy injected by the black hole is enough to offset the radiative losses of the gas, effectively freezing the group in a suspended state where the gas stays hot but does not condense. This is another way in which fossil groups represent an evolutionary endpoint, the natural conclusion of a process where a black hole becomes the primary regulator of the group's fate. In many ways, the black hole in a fossil group is a kind of cosmic monarch, sitting in silent control over a vast empire of hot gas and old stars. Its influence is unseen but pervasive, maintaining order through a balance of heat and gravity. Unlike the chaotic, eruptive AGNs in young galaxies or the dormant ones in isolated ellipticals, the black holes in fossil groups are measured and stable, issuing periodic bursts of energy to maintain equilibrium. They are, in essence, the final architect of silence. Without them, gas might cool, stars might reignite, and the group might stir back to life. But with them, the fossil group remains in its perpetual state of thermal hibernation, a monument not just to the past, but to the enduring influence of gravity, energy, and time. In the grand tale of the universe, these black holes are not destroyers, but curators, maintaining the fragile structure of a fossil group long after its tumultuous beginning has passed into history. They are the silent stewards of entropy, ensuring that what was once a cauldron of collision remains a museum of stillness. Fossil galaxy groups are more than just ancient structures. They are celestial graveyards, places where the tumultuous past of galactic life has come to a quiet, motionless halt. In them, we see the remnants of a once vibrant cosmic neighborhood, now subdued, frozen in time. Their defining features, the solitary giant elliptical galaxy, the absence of bright companions, and the diffuse halo of hot gas, tell a story not just of galactic evolution, but of finality, of a galactic community that has lived, merged, and died. To call these systems evolutionary graveyards is not poetic exaggeration, it is a direct reflection of what has transpired. Fossil groups are thought to have originated from standard galaxy groups, dynamic gatherings of multiple galaxies orbiting a shared center of mass. Over billions of years, these galaxies interact gravitationally, slowly spiraling inwards due to dynamical friction. Smaller galaxies are the first to be consumed, pulled into the central galaxy's grasp, where they are either shredded by tidal forces or directly absorbed in a series of galactic mergers. Bright spiral galaxies with rotating disks, clouds of cold gas, and fields of young stars, all of these are systematically dismantled and digested. This process of galactic cannibalism is neither sudden nor violent in the way supernovae or collisions between galaxy clusters might be. It's slow, inevitable, and driven by the patient tug of gravity. Over time, the central galaxy grows fat on its neighbors, becoming a massive, featureless elliptical, smooth in its light profile, ancient in its stellar population. And as the surrounding bright galaxies disappear, the group loses its visual complexity. What remains are dwarfs and dust, faint satellites, and an endless ocean of hot, X-ray emitting gas. The group, once active and evolving, falls silent. In this silence, fossil groups offer something rare, a glimpse into the endgame of galactic interaction. Most galaxy groups are still busy. Galaxies fly past one another, merge occasionally, pull at each other with tidal arms, and trigger new rounds of star formation. But in fossil groups, that stage is over. There are no more large neighbors left to merge with. The group has run out of participants in its evolutionary drama. It has settled into an equilibrium of entropy, where the gravitational energy of mergers has heated the intergalactic gas and prevented any further condensation into stars. What makes this metaphor of a graveyard so fitting is not only what has been lost, the galaxies, the gas, the star formation, but also what has been preserved. Like an archaeological site buried under layers of time, fossil groups retain clues to their former lives. The extended X-ray halos are leftovers of ancient mergers. Their chemical composition contains elements forged in long-dead stars and scattered by supernovae billions of years ago. Their dark matter halos, still intact and gravitationally massive, are the bones of the structure, holding together a skeleton long after the muscle and motion are gone. Even the central galaxy itself is a monument to what once was. These giants often bear subtle signatures of past mergers, shells, ripples, and diffuse stellar halos, the faint remnants of cannibalized galaxies. Their size and luminosity speak to a history of repeated consumption. These galaxies did not form in isolation. They are the cumulative result of many smaller galaxies, each with its own stars, gas, and identity, now folded into one vast elliptical remnant. In this sense, fossil groups are not only graveyards, they are mausoleums, grand structures built from the remnants of what came before. They carry within them the memory of past cosmic generations. Their silence is not emptiness, but stillness born from completion. They also serve as cautionary tales in the cosmic narrative. They show what happens when galactic growth is too efficient, when mergers occur too rapidly, when feedback mechanisms like black hole heating are too strong or too persistent. In fossil groups, We see what happens when the balance between growth and sustainability is tipped, not into collapse, but into permanent dormancy. Some researchers even speculate that the local group, home to the Milky Way, Andromeda, and dozens of dwarf galaxies, may one day become a fossil group itself. As Andromeda and the Milky Way spiral toward one another over the next few billion years, they will likely merge, forming a single massive elliptical galaxy. The satellite galaxies may be consumed or flung outward. The gas may heat beyond usability. Star formation may cease. And our own cosmic neighborhood could end up in a similar state, a quiet, X-ray glowing relic, drifting through the universe as a ghost of what once was. This fate, quietude after chaos, may be the final chapter for many galactic communities. Not every galaxy will end this way, but fossil groups are a natural outcome of the processes that shape the universe. Their formation does not require exotic physics or rare events. It requires time, gravity, and the conditions that allow for mergers without replenishment. They are the evolutionary graveyards of the cosmos, not because they failed to grow, but because they grew too well, too quickly, and too completely. Now they rest in the long twilight of the universe, massive, ancient, and alone. Imagine drifting through the vast cosmic ocean and coming across a strange island, silent, weathered, and untouched for billions of years. Nothing moves. The winds of star formation have ceased. The once vibrant shores of galaxy interaction are still. And at the island's center stands a towering monument, a massive elliptical galaxy, glowing faintly, surrounded by a hushed halo of X-ray gas. This is no ordinary island. It is a time capsule from the early universe. Fossil galaxy groups are not merely remnants. They are preserved moments in cosmic time, frozen snapshots of galactic evolution that offer us a direct line of sight into a universe that no longer exists. Everything about them, from their structure to their silence, is a clue encoded in light and gravity, waiting to be deciphered. What makes this metaphor so fitting is how fossil groups encapsulate an ancient process, one that happened quickly, early, and left little room for further evolution. They are sealed environments, unchanged in fundamental ways for billions of years. While the rest of the universe has evolved, merged, fragmented, and expanded, fossil groups have remained largely intact, like cosmic amber preserving the dance of galaxies that ended long ago. The central elliptical galaxy in a fossil group is the most prominent element in this capsule. Its stars are ancient, their light now redshifted and dim, tracing their origins back to a time when the universe was young and chaotic. By studying their metallicity, velocity dispersions, and light profiles, we're able to read their memories, like archaeologists brushing away layers of time to uncover fossilized bones. These stars were forged in smaller galaxies that no longer exist, their hosts having been consumed in the great galactic feast that created the elliptical titan we see today. The hot gas halo surrounding the group is another preserved artifact. It retains thermal signatures from the group's formation era. Its temperature profile, metallicity, and entropy distribution carry embedded records of past supernovae, merger shocks, and black hole activity. Unlike the turbulent gas in dynamic clusters or star-forming regions, the gas in fossil groups has long since reached equilibrium. It's not just a halo, it's a thermal diary, etched with the imprint of past energy releases. This sealed nature also makes fossil groups extraordinarily valuable to cosmologists. Because they haven't been disturbed by recent mergers or interactions, their structure is remarkably clean. The distribution of dark matter, the chemical enrichment of the gas, the size and brightness of the central galaxy, all of these have changed little for eons. In them, we find a kind of control group for cosmic evolution. We can ask, what did galaxy groups look like after forming early? How do isolated systems evolve compared to ones that continue to merge? Fossil groups give us controlled answers in a messy universe. They also serve as benchmarks for simulations. In computational models of large-scale structure formation, fossil groups provide a test case for what happens when a group forms early and evolves in relative isolation. If a simulation can't reproduce the observed properties of fossil groups, their deep dark matter wells, their extended gas halos, their star formation shutdown, then it may be missing something fundamental. Fossil groups thus become time-stamped validators of our cosmological theories. There's an eerie beauty to the idea that fossil groups are still telling their stories after billions of years. Their isolation isn't a failure, it's a feature. Their silence isn't emptiness, it's clarity. Like time capsules, they have been sealed by circumstance, formed early in dense environments, consumed their neighbors swiftly, and then sat undisturbed while the universe evolved around them. Inside them, we find cosmic echoes, whispers of starbursts, gas collisions, and black hole outbursts long faded, but not erased. Even the way we discover fossil groups reinforces the time capsule analogy. Optical surveys often miss them, since they look deceptively like ordinary galaxies. Only when we turn our X-ray eyes on them do their true forms reveal themselves, vast halos glowing with fossil heat. These halos are invisible to our eyes, but glaringly obvious to instruments that can see the past in wavelengths we can't perceive. It's like unearthing a buried relic that only special tools can detect, evidence of ancient processes buried under eons of cosmic dust. And perhaps most haunting of all, fossil groups remind us that the universe is aging, not just expanding. They are not early-stage systems caught in the act of becoming something more, they are the final stage. They are what happens at the end of the road, when no more galaxies remain to interact, when no new stars are born, when the light of youth has faded. They are the quiet survivors of a wild, early universe, locked in a form that has barely changed for billions of years. We often think of space as a place of action, galaxies colliding, stars exploding, black holes roaring. But fossil groups flip the script. They are places where the action has ended, where the music has stopped, and only the architecture of the past remains. They are serene, preserved, and unmoved, and in that stillness, they offer something incredibly rare, clarity. So when we look at a fossil galaxy group, we are not just observing a part of the universe, we are opening a time capsule, sent forward from the ancient cosmos, carrying with it the final shape of an evolutionary journey that began before the Earth formed, before the sun ignited, before life emerged. They remind us that everything, galaxies, stars, even the universe itself, has a life cycle. And in that cycle, fossil groups are the archives, the libraries of memory where the stories of cosmic youth are stored, preserved, and quietly told to those who know how to listen. Why do we study fossil galaxy groups, these quiet, ancient, seemingly lifeless corners of the cosmos? The answer lies in the very things that make them so silent, so still, and so strikingly different from the rest of the galactic universe. In a field driven by motion, energy, and change, fossil groups offer something invaluable, a rare opportunity to understand what remains when the dance of galaxies is over, and what that tells us about how galaxies live, interact, and eventually die. Their silence is not a void, it is a record, and astronomers are the archivists deciphering what it all means. Fossil galaxy groups sit at the intersection of several major astrophysical themes: galaxy evolution, gravitational dynamics, dark matter structure, black hole feedback, and the thermodynamics of intergalactic gas. In each of these areas, fossil groups provide a crucial piece of the puzzle. Their importance is amplified by their relative simplicity. Most galaxy groups are messy. They're in the midst of mergers, full of star formation, layered with competing signals. Fossil groups are stripped-down systems, clean, controlled, and settled, making them ideal laboratories for testing theoretical models. One of the most compelling reasons to study fossil groups is that they allow us to trace the end stages of galaxy evolution. In the story of a galaxy's life, we often focus on its birth and early development, how gas condenses, stars form, spiral arms develop, and interactions trigger changes. But what happens in the final act, when the intergalactic stage grows quiet? Fossil groups provide a detailed look at this late-phase evolutionary endpoint, offering answers to questions that are difficult to study elsewhere. What happens when all the major mergers are done? How do galaxies age in isolation? How does a group stabilize after the storm of interaction has passed? Studying fossil groups also sheds light on the cumulative effects of environment, particularly how dense cosmic neighborhoods can accelerate a galaxy's transformation. In regions of high density, interactions happen more frequently and more violently. This speeds up the process of merging, stripping, and heating. Fossil groups are thought to have formed in such dense regions early in the universe's history. Their very existence suggests that galactic environment plays a crucial role in shaping fate. Some galaxies, like those in the field, may continue forming stars for billions of years. Others, like those in fossil groups, are cut short, consumed, quenched, and silenced far earlier than they might have been otherwise. From a cosmological perspective, fossil groups are useful calibration tools for simulations. In numerical models of large-scale structure formation, researchers must replicate the entire range of observed systems, from rich clusters to isolated galaxies to, fossil groups. If simulations fail to produce fossil groups in the correct numbers or with accurate properties, it suggests that something is missing in our understanding of physics, perhaps in how we treat black hole feedback, or how gas cools, or how galaxy mergers unfold. Fossil groups thus serve as natural stress tests for cosmological theories. These systems are also key to probing the influence of supermassive black holes over vast spatial scales. In most environments, it's difficult to isolate the impact of AGN feedback from other energy sources, star formation, stellar winds, turbulence from mergers. But fossil groups offer a unique advantage. They have no recent mergers, no ongoing star formation, and often only a single active galactic nucleus in the central elliptical. That makes them ideal for studying how AGN alone can regulate the thermal state of an entire group's intragroup medium. Observations of hot gas cavities, entropy profiles, and temperature gradients provide vital clues to how these black holes have influenced their surroundings over gigayear timescales. Furthermore, fossil groups help refine our understanding of galactic mass assembly. When we observe the central elliptical galaxies in these groups, we are looking at objects that have grown substantially larger than average galaxies of the same luminosity. This tells us something important about how galaxies grow, not just through star formation, but through the accumulation of other galaxies. Fossil groups show us that cannibalism is a real and dominant mechanism in some environments, and they offer a glimpse of what a galaxy might look like after dozens of mergers over billions of years. They also provide insights into dark matter halo evolution. The deep, relaxed potential wells of fossil groups, inferred from both X-ray gas profiles and weak lensing studies, reveal how early formed halos can evolve into stable structures with little ongoing accretion. The high concentration parameters observed in fossil groups suggest that they collapsed earlier than similarly massive non-fossil systems. This makes them valuable for understanding how halo formation time affects structure, and whether current dark matter models, like cold dark matter or warm dark matter, can accurately replicate these trends. From an observational standpoint, fossil groups are becoming increasingly important as we push toward the era of multi-wavelength astronomy. Instruments like Chandra, XMM-Newton, Rosetta, and upcoming missions like Athena allow us to study the hot gas in incredible detail. Meanwhile, surveys like the Sloan Digital Sky Survey (SDSS), the Dark Energy Survey (DS), and the Vera C. Rubin Observatory's Legacy Survey of Space and Time (LSST) will reveal new fossil group candidates based on their optical properties. As data grows, so does our ability to construct statistical samples of fossil groups, enabling large-scale studies of their demographics, distribution, and evolutionary paths. And perhaps most profoundly, we study fossil groups because they embody the ultimate fate of many galactic environments. They are not rare anomalies, nor are they one-off curiosities. The processes that form fossil groups, galaxy merging, star formation quenching, gas heating, black hole feedback, are universal. Every galaxy group is subject to these forces. Fossil groups are simply those where the process has run to completion. They are destinations on the path of galactic evolution, and by understanding them, we better understand where the cosmos is heading. In essence, fossil groups are the silent historians of the universe. Their stillness is not a lack of activity. It is the accumulated evidence of everything that has happened. To study them is to read the end of a story whose beginning was written in the early universe. And in doing so, we don't just learn about these ancient structures. We learn about all galaxies, including our own, and about the forces that will shape the final pages of cosmic history. The existence of fossil galaxy groups carries with it a hidden message, one whispered across the billions of years since the first light of the cosmos, about how quickly structure must have formed in the early universe. These systems, ancient and quiet as they are now, could not exist in their present state unless galaxies had begun forming rapidly and interacting with one another at surprisingly early times. In a sense, fossil groups are not just endpoints of galactic evolution, they are evidence of a fast-paced beginning. To understand why, we must consider the cosmic timeline. Fossil groups are defined not just by their current properties, but by their histories, and that history had to begin long ago. Observational data and simulations both suggest that many fossil groups formed over 4 billion years ago, with some estimates placing their core formation epochs as early as redshift Z is almost equal to 1 or more. That corresponds to a time when the universe was less than half its current age, a turbulent era marked by high star formation rates, frequent galaxy mergers, and rapid structure growth. For a fossil group to exist today, several things must have already happened very early on. First, a dense region of dark matter must have collapsed gravitationally, drawing in large amounts of baryonic matter, the stuff that makes up stars and galaxies. This protogroup would have formed multiple galaxies relatively quickly. Then, those galaxies would have had to undergo major mergers in rapid succession, with most of the large, bright members being consumed by a central galaxy. This process not only required efficient mass assembly but also little subsequent disturbance. In other words, fossil groups must have formed in dense, but isolated pockets of the early universe, places where matter collected early, but where later accretion of new galaxies was minimal. This tells us something critical about the nature of galaxy group formation in the young universe. If fossil groups are common, and current surveys suggest they might be more abundant than previously thought, then the conditions that create them must have been widespread. That means early cosmic environments had the right combination of density, mass, and timing to drive rapid galactic growth and mergers. Fossil groups, then, are markers of early structure formation, much like ancient fossilized organisms are markers of early life on Earth. They also provide clues about the efficiency of early galaxy formation. The galaxies that merged to form today's fossil central ellipticals must have formed stars and built stellar mass at an accelerated rate. They could not have been slow, passive systems. They had to be actively forming stars, burning through their cold gas reservoirs, and evolving rapidly. Fossil groups are the echoes of that frenetic period, when galaxies burned bright and died young, at least in a cosmological sense. Further support for this comes from studying the stellar populations in fossil groups' central galaxies. These stars are old, often with formation ages exceeding 9 or 10 billion years. Their metallicity levels are high, indicating that many generations of stars lived and died quickly, enriching the interstellar medium with heavy elements before the group fell into dormancy. This star formation history implies that the building blocks of fossil groups, the initial galaxies, must have formed during the universe's first few billion years. Even the hot X-ray emitting gas in fossil groups provides a window into early conditions. This gas is enriched with metals like iron and silicon, produced in the supernova explosions of short-lived massive stars. That means large numbers of such stars must have existed early on, releasing their energy into the intragroup medium during and shortly after the group's formation. The current temperature and chemical distribution of this gas is a preserved signature of early feedback processes, including both stellar and black hole-driven outflows, acting on the group when it was still young and dynamic. Simulations of large-scale structure help flesh out this picture. Models that include early star formation, AGN feedback, and hierarchical merging consistently show that fossil group-like systems tend to emerge in regions that collapsed earlier than average. These simulations reproduce the key features of observed fossil groups only when galaxies are allowed to form efficiently in the early universe. This provides independent confirmation that the presence of fossil groups today is a fossilized record of rapid early evolution, a kind of structural timestamp built into their very fabric. Moreover, fossil groups help test our understanding of galaxy quenching mechanisms in early epochs. The fact that these systems are dominated by old stellar populations and lack star formation today implies that the processes that shut down star formation, heating, stripping, AGN feedback, were already in place billions of years ago. Fossil groups, by reaching their quiescent state so early, prove that environmental and internal mechanisms of quenching were already fully functional in the young universe. In that sense, fossil groups are not just passive relics. They are active constraints on the speed, timing, and conditions of galaxy formation. They help narrow the window of cosmic time in which certain events must have occurred. For example, if we find a fossil group at high redshift, it forces us to accept that its galaxies were born, merged, and quenched incredibly early. Each such discovery refines our cosmological clock, making our models of the early universe more precise and more rooted in observable evidence. And as we push observational frontiers with new instruments like the James Webb Space Telescope, we may begin to detect protofossil groups, systems caught in the act of assembling quickly, well before they fall into the long stillness that defines their fossil phase. These snapshots of rapid assembly will give us even more insight into how the universe evolved from a nearly uniform field of gas into a rich structure of galaxies, some of which grew up too quickly, consumed all their neighbors, and then froze in place, preserved for us to find billions of years later. In this way, fossil groups are not just the final chapter of galactic stories. They also contain the first lines, written in the energetic scrawl of the young universe. They are bridges between the universe that was and the universe that is. Their very existence whispers of a time when galaxies were born quickly, grew fast, and passed into quiet, all before the universe had even reached middle age. In the optical sky, the part visible to our eyes and to many of our most iconic telescopes, fossil galaxy groups paint a deceptively quiet picture. At first glance, they resemble nothing more than an enormous elliptical galaxy, glowing with a diffuse, golden-white light. There's a kind of majestic loneliness to them, a silence not of emptiness, but of completion. But this apparent simplicity hides a profound story that can only be told by carefully reading the light. Because when we peer deeper into fossil groups through optical wavelengths, we begin to see the subtle, almost ghost-like fingerprints of an ancient galactic past. The most prominent optical feature of a fossil group is the bright, massive central elliptical galaxy, often so dominant in brightness that it utterly outshines any of its surviving companions. This galaxy is vast, typically several times more luminous than the Milky Way, with an extended stellar halo that can stretch hundreds of thousands of light-years from its core. Its surface brightness profile follows the classic de Vaucouleurs law, characteristic of elliptical galaxies, but with an excess of light at large radii, a telltale sign of past galactic mergers. This outer light is not uniform or smooth but often exhibits subtle distortions, stellar shells, ripples, or faint tidal streams that are the fossilized remains of smaller galaxies devoured long ago. To the casual observer or the shallow survey, it may seem as though this massive galaxy exists in isolation. But deeper optical imaging reveals a halo of faint satellite galaxies, typically small dwarf spheroidals or irregulars, scattered like forgotten relics around the central Titan. These satellites are not randomly distributed. They often reside well within the group's dark matter halo, tracing the underlying gravitational potential left behind by the original, now merged group members. These surviving companions are dim, sometimes barely distinguishable from background galaxies, and lack the gas and dust needed for new star formation. In essence, they are stellar husks, galaxies that manage to escape the fate of merging, for now. One of the most compelling optical indicators that a galaxy resides in a fossil group is the magnitude gap, the brightness difference between the first and second brightest galaxies in the group. In fossil groups, this gap is unusually large, often greater than 2 magnitudes in the R band, or over 6 times in brightness. This suggests a long period without major mergers. The central galaxy has consumed all nearby rivals, leaving only faint companions far below its brilliance. Such a large magnitude gap is extremely rare in non-fossil systems, making it a key diagnostic tool when identifying fossil groups in wide-field optical surveys. These magnitude gaps are especially useful in massive sky mapping projects like the Sloan Digital Sky Survey (SDSS) or the Dark Energy Survey (DS), where astronomers sift through thousands of galaxy groups looking for candidates. In those vast datasets, the optical signature of a fossil group emerges like a pattern, a solitary bright peak surrounded by a desert of faint points. Spectroscopic follow-up then confirms whether these faint galaxies are physically associated or simply background interlopers. When confirmed, the image becomes clearer, a powerful elliptical, glowing steadily in the twilight of its youth, surrounded by a scattering of dim, orbiting companions, a crown atop a silent kingdom. Interestingly, fossil groups lack the optical chaos found in rich galaxy clusters. There are no sprawling spirals twisting through the field. No bright star-forming clumps, no dusty irregulars undergoing mergers. The lack of optical blue light, a proxy for young stars, is another optical signature of their ancient and quenched nature. Nearly all visible galaxies in the group will have red, old stellar populations. The overall color of a fossil group in composite optical images is therefore golden yellow to orange, indicative of aging stars and passive evolution. But even the light from the central galaxy can reveal subtle complexities. In deep optical surveys, astronomers have discovered intracluster light, faint, diffuse stellar light that doesn't belong to any one galaxy, but drifts between them. In fossil groups, this light is particularly intriguing, as it may represent the last visible remains of galaxies that have been fully stripped or destroyed. These stars, unbound from any galaxy, now orbit the group's core as a kind of starlight fog, too faint to be seen in ordinary images but revealed through long exposures or stacking techniques. The distribution and brightness of this light offer a direct measure of how violently, and how thoroughly, the group consumed its members. Furthermore, deep optical images occasionally show low surface brightness features, such as stellar streams and arcs, that loop or trail around the central galaxy. These are the ghost trails of cannibalized galaxies, the dying echoes of gravitational tides that tore apart smaller systems and spread their stars into long, filamentary arcs. These features are not only visually stunning but scientifically valuable. They allow astronomers to reconstruct the orbital paths and masses of former group members, much like forensic investigators reconstruct a scene from scattered clues. The study of these optical features requires sophisticated tools. Telescopes like Subaru, Gemini, the VLT, and soon the Vera Rubin Observatory allow astronomers to push deeper and capture the faintest structures, down to surface brightness levels as low as 30 mag/arcsec superscript 2. Combined with spectroscopy, researchers can assign redshifts and velocities to the faint companions, confirming their membership in the group and revealing the kinematic stillness of the environment, another hallmark of fossil groups. In summary, the optical appearance of a fossil galaxy group is deceptively simple but profoundly informative. It is a canvas of contrast, the overwhelming brilliance of a central elliptical galaxy set against a sea of faint, whispering companions. No drama. No turbulence. Just light, ancient, stable, and quiet. But for those who know how to look, that light contains an entire narrative of mergers, destruction, domination, and survival. Through the lens of optical astronomy, fossil groups become elegant remnants of cosmic memory, their light a language we are only beginning to fully translate. And in that quiet glow, we see the past, not as it was told, but as it was lived, galaxy by galaxy, star by star, until all that remained was the silence of a final shape, bathed in the faint light of long-dead suns. The central elliptical galaxy in a fossil group did not become a colossal titan overnight. Its size, luminosity, and mass are not the result of a single event, but the accumulated aftermath of countless acts of galactic cannibalism, a slow, relentless, and gravitationally driven feast that unfolded over billions of years. In the absence of cosmic chaos from new infalling galaxies, this massive galaxy has grown not by building from within, but by consuming everything around it. At the heart of this process lies a fundamental mechanism, dynamical friction. When two galaxies move within a shared dark matter halo, especially in a group environment, they gravitationally interact with one another and with the ambient background of dark matter and gas. These interactions create wake-like distortions behind each galaxy, effectively dragging on them, sapping their orbital energy, and causing them to spiral slowly inward toward the group's gravitational center. The more massive the satellite galaxy, the faster this inward migration occurs. Over time, satellites lose angular momentum and begin to coalesce into the core. Eventually, they either merge entirely with the central galaxy or are tidally disrupted, their stars strewn across the group, eventually settling into the central stellar halo. In fossil groups, this process has had millions of years of uninterrupted time to run its course. The result is a central elliptical that's not merely large, it's exceptionally dominant, far brighter than the second brightest galaxy in the group. This extreme luminosity disparity, the so-called magnitude gap, is a direct consequence of a galaxy that has outcompeted and absorbed its rivals. The central elliptical has grown fat on a diet of spiral galaxies, lenticulars, dwarfs, and more, each merger adding to its mass, distorting its shape, and enriching its population with stars of various ages and metallicities. Unlike the violent collisions of rich galaxy clusters, where galaxies slam together at thousands of kilometers per second, the environment of a fossil group allows for low-velocity encounters. This is crucial. In lower-speed interactions, galaxies are more likely to merge rather than just pass by. Spirals, rich with gas and new stars, may be absorbed whole or gradually stripped of their outer layers. Their gas is heated, their structure dismantled, and their identities erased as they are swallowed into the elliptical's glowing body. This slow assimilation is more efficient and complete than in faster-moving, denser environments. Each merger leaves its imprint. Over time, the central elliptical becomes more massive, but also smoother, its structure losing the ordered rotation and disk features of its past components, becoming instead a spheroidal mass of old stars, randomly orbiting within a deep potential well. And yet, for those who look closely, remnants of its feeding history remain. Shells, faint loops, and stellar streams can still be seen in ultra-deep optical exposures, like the scars and stretch marks of a galaxy that has grown not from within, but by consuming its peers. But galaxy cannibalism in fossil groups doesn't just stop at stars. The infalling galaxies also bring with them their dark matter halos, which merge and collapse into the central halo, increasing its mass and concentration. Over time, this creates a deep, singular gravitational well centered on the massive elliptical, one that traps hot gas, bends light via gravitational lensing, and creates the extended X-ray emission that fossil groups are known for. Even the hot interstellar gas from the absorbed galaxies gets added to the group's diffuse halo, slowly heated through shocks and compression until it radiates in the X-ray band, painting the group in an invisible glow. This cannibalistic behavior is so complete that, in many fossil groups, there are no other large galaxies left. The remaining companions are dim dwarfs, far too small to contribute significantly to the mass or dynamics of the system. The feast has ended. The central galaxy sits like a lone monarch on a deserted throne, surrounded by the tattered remnants of a once bustling court. Interestingly, simulations have shown that the rate of galaxy cannibalism is highest in systems that formed early. Fossil groups, by definition, are old structures. They collapsed early, formed galaxies quickly, and began mergers soon after. Because they reside in relatively isolated environments, they haven't been replenished by new infalling galaxies in billions of years. That isolation is part of what allowed the central elliptical to consume its companions without interruption. In contrast, groups and clusters that remain dynamically active, receiving new galaxies over time, often never reach the fossil phase, as fresh material constantly disrupts the process. This evolutionary trajectory offers a fascinating glimpse into the life cycle of galaxy groups. Not all groups become fossils. Some continue merging. Others disperse. But fossil groups represent the case where internal dynamics, rather than external inputs, dictate the outcome. Over time, gravitational interactions favor the growth of one dominant galaxy, which steadily dismantles its peers until it stands alone, not by chance, but by process. This cannibalistic growth also helps explain why central galaxies and fossil groups are so chemically evolved. Merging with many different galaxies brings in stars of varying metallicities and ages. But it also introduces a lot of enriched gas, material that has already passed through several generations of stars. The result is a central galaxy whose chemical fingerprint reflects not a single lineage, but the combined legacy of many, a palimpsest of galactic histories written atop one another. This is the slow galactic feast, patient, inevitable, and complete. Not a burst of chaos, but a long, drawn-out devouring, the universe's quiet version of survival of the fittest. And in the end, the central elliptical remains not just as the winner of this gravitational game, but as the sole storyteller, a glowing archive of all it has consumed. If we could fast-forward the clock of the universe by tens or even hundreds of billions of years, fossil galaxy groups offer a particularly haunting question: what happens to a system that has already grown silent? Unlike dynamic galaxy clusters still bustling with mergers, or isolated galaxies still forming stars, fossil groups have largely finished their transformations. Yet time, gravity, and entropy never stop working. The question becomes, will the central elliptical galaxy continue to grow? Will fossil groups remain fossilized forever, or will they evolve into something else entirely? One might assume the central galaxy will continue to swell indefinitely. After all, it's already absorbed nearly all of its luminous neighbors. But the reality is more nuanced. Most fossil groups today host a central elliptical that has reached a kind of saturation point in terms of major mergers. The remaining satellite galaxies are often ultra-faint dwarfs, low mass and low luminosity, offering little in the way of mass or energy. Even if these dwarfs are eventually pulled in by dynamical friction, their total contribution to the central galaxy's growth would be marginal, perhaps a few % at best. Still, this slow trickle of mass will continue for billions of years. The outskirts of the central elliptical may continue to puff outward, accumulating the stripped stars of any dissolving satellites. Its stellar halo may become even more extended, even more diffuse, eventually blending seamlessly with the intragroup light. In this sense, the central galaxy might not grow brighter but rather more bloated, a slow stretching of its outer envelope, fueled by the ingestion of whatever faint debris still orbits within reach. Over immense timescales, even the dark matter halo itself, that invisible, sprawling structure that holds the group together, may begin to evolve. It will grow more concentrated as dynamical processes cause remaining mass to sink toward the center. But because fossil groups are already dynamically relaxed systems, with little new material falling in, the changes to the dark matter structure will be subtle, more of a slow internal tightening than any dramatic accretion. Another long-term consideration is the fate of the hot gas that envelopes the group. Currently, this gas glows brightly in X-rays, thanks to its temperature of tens of millions of degrees. Over trillions of years, however, without fresh energy injection from mergers, supernovae, or active galactic nuclei (AGN), this gas will gradually cool. But not in the way we might expect. The universe's expansion will continue to stretch and thin the gas, reducing its density, lowering its temperature, and eventually dimming its X-ray brightness beyond detectability. In the distant future, fossil groups may lose their defining glow, becoming invisible in the X-ray sky. What about the central galaxy's black hole? Right now, the supermassive black hole at the core of the elliptical galaxy may still flicker occasionally with low-level activity. But with little gas to accrete, and no major inflows expected, it will likely go dormant. It will remain a silent giant, dark, cold, and inert. Yet it will still influence the structure of the group subtly, its mass anchoring the galaxy's core and perhaps guiding the eventual fate of stars and stellar remnants that fall into its gravitational grip. And then there's the cosmological horizon to consider. As the universe continues its accelerated expansion, driven by dark energy, galaxies not gravitationally bound to the group will recede faster and faster, eventually becoming inaccessible. Fossil groups, already isolated, will become even more alone, with no new galaxies ever entering their domain. They will be like cosmic islands in an ever-darkening sea, cut off from everything else by the expansion of space itself. Over unimaginable stretches of time, the stars themselves will age. Red dwarfs, the slow-burning embers of stellar evolution, will eventually burn out. White dwarfs will cool. Neutron stars and black holes will drift silently. The central galaxy of a fossil group will become a collection of stellar corpses, slowly darkening as the last flickers of starlight fade. The fossil group will persist, not as a glowing structure, but as a cold, gravitational relic, its energy spent, its story already written. And yet, it won't disappear. Fossil groups are deeply bound structures, gravitational wells carved early in the universe's history. Even as entropy increases and the universe trends toward thermodynamic equilibrium, these structures will persist as the final architectures of galaxy evolution. In a far future universe where little remains active, fossil groups, or what's left of them, will be among the last coherent structures still bound by gravity. Will the central galaxy ever truly stop growing? Practically, yes. The environment offers no new large galaxies to consume, no gas to form new stars. But gravitational dynamics are patient. Some future dwarf galaxies may still spiral in. Some rogue stars may be pulled into the galaxy's halo. Tiny black holes or stellar remnants may drift inward. These events will be exceedingly rare, but over timescales of quadrillions of years, even these whisper-quiet processes leave their mark. Eventually, what remains is a cold monolith, a galaxy without gas, without new stars, surrounded by the skeletal remains of the cosmic structure that birthed it. No longer glowing in optical or X-ray. No longer evolving in any meaningful way. But still existing. Still massive. Still bound. And in that stillness, the fossil group becomes what its name always hinted at, not just a relic of the past, but a preview of the far future. A glimpse into what awaits all groups, all galaxies, when time has had its final say. Not a place of action, but of memory. A structure that persists not to change, but to remind, of what once was, of how galaxies lived and died, and of what remains when everything else has moved beyond reach. Fossil groups provide a striking case study for one of the most fundamental transitions in the life of a galaxy, the moment it stops forming stars, a process astronomers call quenching. In these silent systems, the engines of star birth have long since shut down. Their galaxies are filled with old, red stars and have no vibrant blue glow of young stellar populations. To understand how this came to be, we need to explore the relationship between fossil groups and the quenching mechanisms that turned vibrant galactic ecosystems into stellar graveyards. In the early universe, galaxies thrived on cold gas, the raw material from which stars are born. This gas, often drawn in from the cosmic web or acquired through mergers, would settle into rotating disks, cool down, fragment, and ignite new generations of stars. But in fossil groups, this gas has largely disappeared. The process that led to this disappearance, this drying up of the galactic fuel supply, is the key to understanding how these systems were quenched. One major contributor to quenching in fossil groups is the shock heating of infalling gas. As galaxies collide and merge within the group's deep gravitational well, their interstellar gas is subjected to violent compressions, shocks, and turbulence. Instead of cooling and settling into new stars, this gas is rapidly heated to tens of millions of degrees, forming the vast X-ray halos that now surround the group. Once the gas is this hot, it becomes extremely difficult to cool back down, the cooling times stretch to billions of years or more. Without cold gas, star formation grinds to a halt. This heating is especially efficient in fossil groups because of their early formation and isolation. Since they collapsed early in the universe's history and experienced their major mergers billions of years ago, they had ample time for their gas reservoirs to be shock-heated and stabilized. Unlike active groups and clusters that continue to receive fresh, cold gas from outside, fossil groups became thermally sealed environments, effectively cutting off the supply chain for star formation. In addition to shock heating, another powerful force in quenching is AGN feedback, the release of enormous amounts of energy from the central supermassive black hole in the dominant elliptical galaxy. As matter falls into the black hole, it doesn't simply vanish. It radiates energy outward in the form of powerful jets, winds, and radiation. This energy can heat or expel the remaining gas in the galaxy, further preventing cooling. In fossil groups, where mergers have funneled enormous amounts of gas and matter into the central galaxy, AGN activity was likely intense in the past. These black holes may have sterilized their surroundings, injecting enough energy into the group's core to create a long-lasting state of thermal quiescence. There's also strangulation, a more subtle but equally effective quenching mechanism. As smaller galaxies fall into the fossil group's halo, they encounter the hot, dense intergalactic medium. This medium acts like a pressure cooker, stripping away the outer gas halo of the galaxy, a process called pressure stripping. While the galaxy may retain its cold internal gas for a while, it loses the ability to replenish it from the cosmic web. Over time, star formation slows and then ceases entirely. In a fossil group, this process plays out repeatedly across multiple satellites, gradually transforming once active galaxies into red, passive remnants. All these processes, shock heating, AGN feedback, pressure stripping, and strangulation, are more effective in fossil groups because of their relaxed and aged structure. The absence of new major mergers or infalling galaxies means the group can maintain a stable, hot atmosphere, which in turn ensures that cold gas is continually suppressed. This feedback loop creates a self-sustaining quenched state, where every mechanism reinforces the others. Observational evidence confirms this story. Spectroscopic studies of fossil group galaxies reveal old stellar populations, often with average ages exceeding 9 or 10 billion years. Their spectral features show no signs of recent star formation, no strong H-alpha emission, no ultraviolet excess, no dust-obscured starbursts. In essence, fossil group galaxies are some of the most thoroughly quenched systems in the known universe. And yet, this quenching doesn't just affect individual galaxies, it defines the entire group. Unlike galaxy clusters, which often contain a mix of blue, star-forming galaxies and red, quenched ellipticals, fossil groups show a remarkable uniformity in color and activity. The central galaxy is red. The satellites are red. The group as a whole radiates a pale, passive glow, a glowing tomb of once active systems. Understanding this group-wide quenching is important because it mirrors processes happening across cosmic time. As the universe ages, more and more galaxies are joining the red sequence, the population of quiescent, elliptical galaxies that no longer form stars. Fossil groups serve as early examples of this transformation, natural laboratories where we can study how and why galaxies stop growing. By examining them, astronomers can better understand how environments accelerate or delay galactic aging, and what that tells us about the future of cosmic structure. In fact, fossil groups may represent the fate of many galaxy groups, including our own. As mergers slow, gas supplies dwindle, and black hole feedback grows, more systems will enter the same thermally stable, quiescent state. In this way, fossil groups are not anomalies, they are forerunners. Their quiet, quenched existence is a preview of what lies ahead for galaxies across the cosmos. So while the light from fossil groups may appear dim and steady, it tells a powerful story of star-forming youth brought to a close by environmental forces, of gas turned to plasma, of galaxies suffocated by the very structure that once gave them life. In their stillness, they reveal the mechanics of cosmic death, not in violent explosions, but in the slow cooling of a system that has simply run out of fuel. It's an almost unsettling thought that the local group, our cosmic neighborhood containing the Milky Way, Andromeda, and dozens of smaller galaxies, might one day become a fossil group itself. Could our corner of the universe be on a slow trajectory toward the same silent fate? As it turns out, the answer is not only possible, it's surprisingly plausible. The conditions that define a fossil group may very well be the natural end state of the local group, billions of years from now. To explore this, we need to first recall what makes a fossil group a fossil. At its core, it's a galaxy group that has undergone most of its internal evolution early on. Its large members have merged into a single, massive central galaxy, leaving behind only faint, scattered companions. It's surrounded by a halo of hot X-ray emitting gas, and shows no signs of recent star formation in its dominant galaxy. Importantly, it is gravitationally self-contained, not receiving significant infall from the broader universe anymore. The local group already exhibits many of these ingredients in their early forms. It's a gravitationally bound structure, containing over 50 known galaxies, with the Milky Way and Andromeda as its two giants. It has a population of small dwarf galaxies, including the large and small Magellanic Clouds, as well as dozens of ultra-faint companions that orbit the two major galaxies. Most of these dwarfs are gas-poor, old, and no longer actively forming stars, a fossil-like trait already manifesting. But the key to a future fossil group lies in the fate of the Milky Way and Andromeda. According to the most precise measurements from the Hubble Space Telescope in Gaia, these two galaxies are on a collision course. They are expected to begin interacting in about 4 billion years and fully merge within roughly 5 to 6 billion years. The result will be a gigantic elliptical or lenticular galaxy, sometimes informally dubbed Mausoleums. This single, merged galaxy will dominate the local group, absorbing not only the stellar mass of the Milky Way and Andromeda but potentially pulling in many of their satellites as well. This future Mausoleum galaxy would fulfill the first condition of a fossil group, one dominant central elliptical formed through the merging of the group's brightest members. Over time, the gravitational interactions with remaining dwarfs and minor galaxies will lead to more mergers, either through direct collisions or tidal disruption. This will increase Mausoleum's mass and the size of its stellar halo, gradually widening the magnitude gap between it and the next brightest surviving companion. But what about the X-ray halo, the hot gas that's a defining characteristic of fossil groups? Here too, we see reason to believe the local group could eventually meet this criterion. While it doesn't currently host a strong X-ray emitting intragroup medium like massive fossil groups do, the merger between the Milky Way and Andromeda will likely generate enormous amounts of thermal energy. Gas clouds from both galaxies will collide, compress, and heat up, creating a massive reservoir of hot, X-ray emitting plasma. Supernova feedback, black hole activity, and the shock heating from the merger itself could maintain a diffuse, ionized halo for billions of years. Moreover, the local group resides in a relatively low-density cosmic environment. While it's part of the broader Virgo supercluster, it's not in a highly populated region. As the expansion of the universe continues to accelerate, nearby groups and galaxies will move beyond the cosmic horizon, receding so fast that they'll become unreachable even at light speed. Eventually, the local group will be isolated, sealed off by the expansion of space. No new galaxies will fall in. No new material will disrupt its structure. It will become, quite literally, an island universe. In such a setting, Mausoleum will reign alone. The remaining dwarfs will either have merged or settled into stable orbits, slowly stripped of any gas or stars they still hold. The hot gas will cool slowly, the stellar population will age, and no new stars will form. Star formation will decline then cease. The light will grow redder. And the local group will enter a new phase, quiet, still, and ancient. By the traditional definitions used by astronomers, this future structure would meet the core criteria of a fossil group: a large magnitude gap between the brightest and second brightest galaxy, a dominant central elliptical, a quiescent star-forming environment, and likely an extended X-ray halo formed from merger activity. It may not be as massive or luminous as the most prominent fossil groups observed today, but in form and function, it would be indistinguishable. It would be a fossil, and we would live in it. This leads to an eerie realization: we are part of a story that's already being written, one that ends in silence. The vibrant star fields of the Milky Way, the blue arms of Andromeda, the active birthplaces of new suns, all of these are temporary. In their place will be a vast, red elliptical galaxy, serene and static, glowing softly in a universe that grows colder and darker with time. Fossil groups are not just curiosities in the night sky, they are windows into our own future. When astronomers observe them, they are not merely looking at the past. They are, in a sense, seeing ahead. And in those ancient, quiet giants, surrounded by nothing but faint companions and hot gas, we catch a glimpse of what the local group is destined to become. So yes, the local group is on the path toward fossilization. One day, long after our sun has died and even after Earth has been consumed or frozen, Mausoleum will float alone in an empty sky, wrapped in X-ray mist, surrounded by the ghosts of galaxies it once knew. And though no conscious observers may remain to witness it, the fossil it becomes will carry the story of where we came from, and where all galaxies may eventually go. Even with all we've learned about fossil galaxy groups, their defining traits, their origins, and their eerie silence, a host of unanswered questions still lingers in the vast dark between stars. These systems, while seemingly understood in principle, continue to provoke astrophysical curiosity. For every fossil group we identify, a new puzzle seems to emerge. Why do some galaxy groups fossilize, while others remain dynamic and active? Are fossil groups the rare exceptions to a cosmic rule, or are they the quiet majority we've simply failed to notice? These questions pull at the seams of our understanding of galaxy evolution, inviting us to probe deeper. First and foremost is the fundamental mystery of divergence. What causes some galaxy groups to follow the fossil path, while others continue to merge, collide, and evolve for billions of years? At first glance, many groups in the early universe formed under similar conditions, concentrations of matter collapsing under gravity, forming galaxies that cluster together. Yet only a subset of these groups end up becoming fossilized relics, with one dominant galaxy and a sparse halo of faint companions. Why? One possibility is initial density and collapse timing. Some groups may have formed in especially dense regions of the early universe, where gravitational collapse happened faster and earlier than elsewhere. In these cases, the galaxies within a group had more time to merge and stabilize before the cosmic environment evolved further. But this idea doesn't always hold up. Some groups in equally dense environments never reach a fossil state. It's not just where or when a group forms that determines its fate. There must be other variables at play. Another factor might be the merger history and gas content of the group. Perhaps fossil groups form from early, gas-rich mergers that consume their star-forming fuel quickly, heating up the surrounding gas and quenching future star formation. Other groups may experience more fragmented, lower-energy interactions, allowing galaxies to retain their gas and continue forming stars for longer. But this explanation also leaves gaps. Observations show that some fossil groups still retain large gas halos long after their galaxies have gone quiet. So the presence of gas alone doesn't determine activity. There's also the potential influence of supermassive black hole activity. Could the strength and timing of AGN feedback, the release of energy from the central galaxy's black hole, be the decisive trigger for fossilization? A single well-timed blast of AGN-driven wind could heat up the surrounding gas enough to halt further cooling and star formation across the entire group. But AGN activity varies widely even among similar systems, and fossil groups don't always host especially active or massive black holes. This adds to the uncertainty, suggesting that fossilization may result from a confluence of many small events rather than a single dominant cause. Another unanswered question is more observational. How many fossil groups are still hidden from us? Our current census of fossil groups is limited by technology and by the selection criteria we use to identify them. Most fossil group surveys rely on optical and X-ray observations, which are often biased toward relatively nearby systems or those with especially bright X-ray halos. That means there could be hundreds or thousands of faint fossil groups lurking in the background of deep sky images, invisible until we know what to look for, or until our instruments improve. Furthermore, as we explore deeper into space and look farther back in time, we must ask, how early did fossil groups begin forming? Are they a relatively late-stage phenomenon, or did some form as early as a few billion years after the Big Bang? If the latter is true, then fossil groups could serve as time markers for the earliest galactic assembly, anchoring our models of structure formation in the early universe. And then there's a more nuanced mystery. Are all systems we label as fossil groups truly fossilized, or are we seeing them in transition? A group may appear to be fossil-like today, one dominant galaxy, a large magnitude gap, and a quiet environment, but in a few billion years, it could be disrupted by the infall of new galaxies or reignited by some unexpected event. In this sense, fossil may be a temporary phase, not a permanent state. The fossil label implies a kind of finality, but perhaps the universe is less settled than we assume. This leads to a broader philosophical puzzle that haunts all of cosmology. How do we interpret stillness? When we look at a fossil group, are we seeing the end of a story, the conclusion of galactic drama? Or are we simply catching it in a slow chapter, part of a larger, longer tale whose next twist hasn't arrived yet? Even the classification of fossil groups itself is somewhat arbitrary. The defining threshold, a magnitude gap of 2 or more between the brightest and second brightest galaxy, is a human-made boundary, chosen for convenience and statistical clarity. But real systems are messier. Some groups fall just short of the criteria and are excluded from fossil catalogs, even if their physical processes mirror those of canonical fossils. This raises the question, are we missing fossil-like systems because of how we define them? Could a more nuanced or dynamic classification yield a deeper understanding of how widespread this evolutionary pathway truly is? And what of the role of environment? Are fossil groups more likely to form in isolated regions of the cosmic web, where outside interference is minimized, or are they scattered more randomly across the universe? Studies offer conflicting answers. Some fossil groups appear in relatively quiet neighborhoods, but others are embedded within larger filaments, or near active clusters. The connection between large-scale structure and fossil formation remains murky. Ultimately, fossil galaxy groups present us with a paradox. They are quiet, but deeply mysterious. They are still, yet full of motion in the past. They seem simple, a central galaxy and a faint halo, but represent one of the most complex evolutionary outcomes in cosmic history. For every fossil group we study, we're left with questions that push at the edges of our cosmological understanding. Why do some galaxies consume their neighbors and fall into silence, while others remain vibrant? How many such systems lie hidden beyond our current reach? And what might they reveal, not just about the past of the universe, but about its future? Fossil groups are more than remnants. They are cosmic riddles, frozen in time, waiting for us to read their clues. In the vast silence of space, fossil galaxy groups whisper of a violent past now turned still, where galaxies once danced and now drift alone. These immense, quiet structures are not just clusters of stars orbiting a gravitational center. They are echoes. Fossil groups are the last breath of chaotic formation, the skeletal architecture left behind after the music of galactic mergers has faded into a cold, cosmic hush. What was once a stage of spirals and collisions, luminous with newborn stars and turbulent with plasma tides, has faded into a single brilliant centerpiece, the lone survivor of countless encounters, ringed by faint shadows of what came before. Each fossil group is a monument to time, to the relentless march of gravity and entropy, to the unhurried sculpting of structure across billions of years. The central elliptical galaxy, bloated and brilliant, is not merely a survivor, it is the composite memory of all its former companions. Their stars now orbit as one. Their identities lost, but their mass preserved. Like a mythic creature made of ancestors, these galaxies wear their past in silence. And all around, the X-ray halo glows, not with life, but with heat. With the memory of the energy released when gas was shredded, compressed, ignited. It glows like a final ember in a fireplace long since cooled, a ghost light marking where fire once raged. The hot gas that now floats gently between the galaxies is the result of trauma, shock-heated, stirred, and sealed within the group's grasp. No longer able to cool and coalesce, it denies the possibility of renewal. Star formation has been turned off not with violence, but with a suffocating calm. To look upon a fossil group is to gaze at a paradox, the stillness of death born from the chaos of life. No supernovae light the sky here. No brilliant arms of spiral galaxies twist with gas and starlight. Only the slow, graceful orbiting of satellites too dim to matter, too sparse to challenge the rule of the central monarch. These are the graveyards of the cosmos, not in ashes or ruins, but in majestic quiet. And yet, within that quiet lies the ultimate story, of how the universe builds and breaks, assembles and absorbs. Of how galaxies, like empires, rise and fall, only to leave behind a single survivor, vast, luminous, and alone. These survivors drift in an expanding cosmos that will one day stretch so far, so wide, that even light from neighboring systems will be lost to the darkness. Fossil groups are, perhaps, a preview of the fate that awaits us all, when the last galaxies have merged, and the cosmic dance has ended. They are the punctuation at the end of long galactic sentences. And still, they endure. They endure as relics of the universe's youth, as signposts for its age, as tombstones etched with the history of countless stellar generations, as reminders that even in the emptiness, there is form. Even in silence, there is story. So when we look into the night sky, past the flicker of stars, past the haze of nebulae, past the clusters that still burst with life, we may find, tucked in the deepest reaches of space, a single galaxy glowing alone, surrounded by shadows, wrapped in gas, and whispering faintly of the countless galaxies it once devoured. A whisper that says, "Here galaxies once danced, and now they drift alone." This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.